हेलो हेलो। ठीक है।
हेलो हेलो।
Hello. Hello. All participants are going to start our meeting very soon. A very good morning to everyone. I am Aitya Patra on the behalf of National Institute of Technology Rourkela. Welcome to all the participants on the fifth day of High-End International Workshop Karyasala. We are here going to begin today's morning session on integrating innovations with cost effectiveness for competing electromagnetic energy assisted food processing and packaging technologies. On this, Professor P. Balasubramanian and Dr. Pritam Sarkar will be presenting their respective lectures. First, I would like to invite Professor Balasubramanian, who is currently working as Assistant Professor at the Department of Biotechnology and Medical Engineering in National Institute of Technology, Rourkela. He has acquired graduation in biotechnology from Anna University, Tiruchirappalli, MTech in Environmental Management from Anna University, Chennai, and PhD in Environmental Biotechnology from IIT Madras. His research focus includes environmental biotechnology, bioprocess technology, bioengineering, sustainable development, and many more. He has authored over 116 publications in reputed journals and book chapters. He is a member of International Bioprocessing Association, Biotech Research Society of India, and Biochemical Technology Society. Thank you, sir, for being here. I would like to request you to present your lecture about microwave-assisted drying and pyrolysis, process kinetics and its mechanism. Over to you, sir.
Thank you for this opportunity. Yeah, very good morning to one and all here. Okay, so today I'm going to discuss about the microwave-assisted drying and pyrolysis of biological product or agro residues with reference to process kinetics and its mechanism. Okay, especially for those who are in online. Okay, I would like to welcome you all to this beautiful campus in near future. And we are in the eastern part of the country. And we have a very beautiful campus. So in near future, you are most welcome to visit our campus. And coming to our group, we are mainly working on 3 different domains. One is on food, energy, and water. Okay, in case of food, either probiotics with reference to kombucha beverage, or we are dealing with some macroalgal seaweeds as a source of prebiotics. Okay, and in case of energy, biosecretion of carbon dioxide with the help of algae or char. And in biorefinery, bioethanol or biodiesel, some kind of biofuels that we are trying to explore. The point is, like, even these 3 things seems to be a kind of independent entity, but in general, it's going to be interlinked. So that is why, like, we are trying to understand its nexus. That is the very long-term goal, because like food, if you would like to make without energy, you can't make food. Okay, the same way, like energy and water is also being linked. If you want water, energy has to be spent to pump out the water. Okay, so likewise, what are the food that we take that is having a virtual amount of water involved in it? So all these 3 things have been so far seen as a separate entities, but right now we are trying to put it all together in order to attain the sustainable development goal, especially the number 2, attaining zero hunger. Okay, so how we could able to make the food secure to all the human population that's happening in this globe, because of the current climate to get escalated very several food. Okay, by 2050 we are going to reach 9.2 billion people, and how are we good able to ensure the availability of food to each and every person? That is what we are trying to deal with. So which in fact going to focus on have impact on people, the environment, as well as on our day-to-day economic activities. So earlier people were focusing on the developmental aspects at the cost of environment, but right now we are trying to attain this triple bottom line of sustainable development goals to ensure the societal development, economical development, as well as environmental development. So that is why like we are trying to focus on this particular aspect. Okay, so coming to today talk, like we are going to focus on downstream processing techniques. Like so far, we are mainly working in upstream processing. This is not our cup of concern, but still a pinch of salt that we have been added to this drying technique from our lab. So that I'm trying to explain today. For last 4 days, you people have continuously heard about what is drying and how it is being happening, what are the different types. So I will just simply rush it up to the introduction part, and then I will just mainly focusing on like why microwave drying has to be focused, okay, and how it can be helpful to process any of the biological products. Okay, say apart from food product and agro residues, how it can be used for biological products also, say microbes or microalgae kind of stuff, how without losing its nutritional value or aroma or any other high content, without loss of those attributes, how we could able to dry the same biomass, that we will be checking out. And even I will be explaining 2 more case studies that from our own lab, how we have utilized the current techniques such as machine learning, okay, or like new emerging algorithms to find out its correlation between the input and output parameters and understanding its overall kinetics. So that is how the today travel will be there. So in case of drying, it will be having both integrated heat transfer and mass transfer. The heat has to get travel from outside to the core of your substrate. Okay, that is how the moisture content would be able to get released out from the center of the substrate to the outer space. Okay, so we have to dry it so that we could able to avoid the further microbial growth, so that we could able to avoid the reduction bulk weight, and we could able to store it for quite long time. This is why we have to go for drying, and how it is being happening, how you would able to find out the rate, all those things, like at least you people might have been aware. And need not to say that there are several techniques available, like you can simply put it under sun. Through sun drying also it can be possible. We could able to remove the moisture content, or we can force it through a convective air. Through hot air also we could able to dry it, or we can make the drying either through contact. Okay, that is also can be possible. And apart from these conventional techniques, right now many other electromagnetic radiation based techniques also coming. For example, infrared, it need not to be get in touch with the substrate that has to be dried. Rather, even through convective mode, it can be dried out. But still, people are focusing on freeze drying and other parts of other types of drying. Okay, conventionally for biological products, most of the time freeze drying is being used. Okay, but the problem with that is like it will be having very long exposure time. Okay, so we can't wait for that much time to process our biomass, especially the biological products which are very high sensitive to heat. Okay, so that's why like this particular dielectric heating or microwave heating is coming into the picture. And even these kind of things have been right now in practice in many industrial scale applications. So all these things you people might have been get introduced over the last couple of days. So the problem with the other types of heating, and why or under which circumstance when we have to go for this dielectric heating, because like in other cases either it will be a kind of quite energy intensive, or it might be much more time consuming. Okay, so in industrial scale of operations we can't wait for that much time, or we can't be so energy intensive process. So in order to reduce the overall cost of any biological product, we are mainly focusing on this particular dielectric drying, microwave drying kind of thing. So the uniqueness with this microwave drying, like it would able to heat the complete material in a uniformized way when compared to convective heating. Okay, so in case of convective heating, the heat will be passed from out to in, but in case of microwave heating, the heat can be start from center and it go out. So that is how the process are becoming much more faster. Okay, so in case of industrial drying, like we could be able to go for much faster with less energy intensive process, with less cost, but still without getting compromised on the quality of product that we are going to make. That is why like we are very much focused on this kind of microwave based drying. Like you might understand that it needs some kind of absorbers, okay, or like based upon the availability of water, it would be able to heat up the substance much faster, and that is how like it is intensifying the drying process quite efficient. Okay, like it will make the dipoles to oscillate. So that is how like it will make the distribution of heat in much more efficient manner. So within less time, we could able to attain the same efficiency instead of waiting for quite long time. So this is the overall advantage that we have with reference to dielectric heating. We could able to attain the same loss in moisture content within very less span of time. Okay. So even based on the availability of moisture content, like it have different types or different mechanisms being involved in drying the product. Like in case of any food products, also we will be mainly focusing to bring down the moisture content less than 10% or maximum 15%. So how we could able to reduce the moisture content with very less span of time? So that is where we have been working on. But the problem is like it have some disadvantages also. Like for example, when the particles that we are going to dry out, okay, if it is having like non-uniformity in its shape, okay, then this dielectric heating might have some disadvantages. For example, in this condition, the microwave get decays from while traveling from outer periphery to inner side. Okay, or like here it will be having exponential decay. Suppose if you are giving a microwave from two different directions, then it might overheat also. So the point is like whether what is the source of that microwave heating, in which direction it is going to be get impacted on the substrate, and where are we going to keep our material that going to get dry. All these things going to impact the overall efficiency of drying. And there are several mass transfer models available for understanding the microwave drying, and mostly based on empirical or diffusion or heat transfer models, like to understand the mechanisms involved in that as well as the kinetic. Because being a engineering, we would like to finally address the question how fast the process would be able to happen, or how much time I have to wait in order to get the product dried for my desired conditions, or how much money I have to spend in so that I could able to get the desired product without losing its product attributes. So understand that we have to even look in terms of modeling aspect. So it has some of the obstacles that we have discussed so far. So with this background information, let me take you to the case studies like that we have been worked out in our lab. Like for example, here I'm going to explain about like microwave drying of algae, microalgae. Okay, so why do we have to dry the microalgae, and then what methodology that we have been adapted, and then how we found out the kinetics, and what is the take-home message out of this particular study that we have carried out. That is what we are going to discuss right now. Like as we know, like there are several biological products, okay, coming out in market, okay, which has to be also get dried. So what we are doing, like we are cultivating the algae, microalgae in a very larger quantity. So this one is say around 40 liter capacity, or even we do have in our lab around 1500 liters capacity. So the point is algae is being cultivated, okay, and then it is in a liquid water medium, so that has to be separated out, and that has to be further dried out to make it as a final product. So in case of any biological products, it will be having two techniques such as upstream processing, as well as another one is called is downstream processing. So how a substrate is getting converted into a product, that is what all about upstream processing. Once that is being done, with that our job is not going to get over. Rather, after that, how are we going to recover those biological products? Okay, and how are we going to purify it? How are we going to concentrate it? How are we going to dry it to make it as a final end product? That is where the huge engineering challenges lies. Okay, as far as biological or biotechnology is concerned, upstream processing maybe seems to be quite relatively little easy, but the downstream processing is going to dictate the overall cost of the product. So if you could able to come up with much more sophisticated technique to dry out the material without losing its product attributes, that is what we are looking for. So in case of algal, we just concentrated, we thickened the slurry so that it has been brought down to 70 to 80% moisture content. But the challenge is, how are we going to bring down the moisture content from 80% to 10%? So that is where we are looking for a drying technique. So it shouldn't consume more energy as well as your process cost, as well as it shouldn't consume more of your time. So that's where we taken the help of microwave. After going through several literature reports, we designed our scope of work in such a way that, like, this 80% moisture has been brought down to further 33% by just centrifugation. Okay, so this is also another unit operations, okay, through which we could able to bring down, or we could able to concentrate the biomass in much better manner. So from 80% moisture content, now it is being brought down to 33% moisture. Then after, from here, how are we going to bring down to 10% with the help of microwave? That has been tried out with two different techniques. One is all about like a conventional convective hot air oven. Just we are forcing the heat air to pass through a material to get it dry. Okay, that is one way that can be done at 40 degrees Celsius to 100 degrees Celsius. But we have to keep in mind that the moment we scale up the temperature, we rise up the temperature, it might have some negative impact on our bioactive components. Okay, so it's not only all about drying out the algae, rather drying out the algae without losing the nutritional value present in it, without losing its aroma value present in it. So we have to always have a trade-off between the drying conditions as well as the product attribute that we are looking for. So in case of convective air oven, like we can vary the temperature from 40 to 100 degrees Celsius. And in case of microwave oven, we varied the power intensity from 360 to 900 watts, so that we could able to get the dried microalgae. So during these experimental observations, what are the things that we learned, that we are trying to put it to understand the mechanism of drying, as well as to understand its kinetics, drying kinetics, so that we could even able to evaluate whether this process is energy intensive or comparably fine. Like, what is the overall energy consumption of this particular drying technique? That also we could able to evaluate. So that is what overall scope of the study. Okay. So finally, we are trying to understand its algal lipid content. So the point is, like, we are trying with two different techniques. One is the conventional way, and another one is the microwave technique. Okay, through which, like, where we could able to get the drying much faster with low cost, as well as without losing our product attributes. Okay, so there are several equations that is being used to understand its kinetics. Like, for example, how to check the moisture content, how we could able to understand the drying rate. Okay, and what is the energy that is being involved in that. Okay, like all those things we could able to check out with these mathematical equations. So these are the experimental observations for hot oven and drying. Okay, like in case of hot air oven drying, like we have been varied the temperature from 40 degrees Celsius to 100 degrees Celsius, 40, 60, 80, 100. So as obvious, like the 100 degrees Celsius took very less time. Within a less span of time, it would able to get dry. Okay, so those things we try to understand the kinetics as well as the heating rate. Okay, then similarly we have done for microwave oven drying, but in case of microwave oven drying, like the heating intensity, okay, that is being power intensity has been varied from 360 watt to 900 watts. Okay, and as expected, in case of 900 watts, the time taken was quite less. Okay, as you increase the intensity of heating, obviously the drying rate will be much faster. But the point is, without getting compromised on the quality of the product that we are looking for. So it's not only all about drying the product, rather, apart from drying the product, whether it have any impact on my final product attribute. That is what I have to look for. So first we try to understand the drying kinetics. So how effective in diffusing of heat from the source to the substrate, because until unless the heat is getting transferred, the mass, that means the vapor, that wouldn't get evaporated. So it is a kind of integrated heat transfer as well as mass transfer process. So we have to understand both the process in a coupled manner. Okay, so that is why we are very much interested in understanding the diffusivity coefficient and how much energy is being got, so that we could able to get the overall calculation energy. So which is quite higher for microwave drying, which makes the process much more better. Okay, and then like the same experimental observations have been fitted into several mathematical expressions to get the overall kinetics that is being involved in that. For example, this is for microalgal drying through convective drying. Okay, it has been done with several mathematical models such as Page, Newton, Anderson, Babbies. Okay, to check out the moisture removal rates. Okay, so that we could able to get like whatever the experimental observation that we made, that we are trying to fit into these models to check out the best fit of a mathematical expression, so that we could able to learn what exactly being happening inside the process. Okay, so that can be checked out with these kind of statistical parameters such as correlation coefficient or root mean square error or chi-square, any of these attributes that we can take into the consideration to check out how best the mathematical model would be able to explain our experimental observations. So we learned that like based on the R-square value, like which kinetics would able to best explain the experimental observation. Similarly for microwave drying also. So the point is we try to compare the conventional convective hot air oven drying technique as well as microwave based drying technique, so that we try to learn like how much energy is being involved in this process, whether it is a really energy intensive or we could able to save some energy, because 1 unit of energy that I am going to save is almost equal to 1 unit of energy that I have produced. Okay, so how we could able to minimize the energy consumption for drying process, as well as without getting compromised on the time that being involved in it. So we try to even correlate with economical value, because at the end of the day, if you would like to convince anyone from the industry, you have to talk in terms of economical value. Okay, so how much money they could able to safeguard through this drying technique, that also has to be evaluated. And apart from that, societal or environmental benefits. Okay, like by switching over from this technique to this technique, what will happen? How it is going to contribute to the safeguard of the environment, even those aspects like greenhouse gas emission, all these things have been computed, and then we compared between the convective and microwave based drying. And coming to the very last aspect, it's not only about the drying, rather without getting compromise on the quality of product that we are making out. So in case of this particular microalgal drying, like we are very much interested in the final lipid content. Okay, so we try to understand like apart from the influence of temperature on drying, how it is going to impact my product attribute. So as observed, like while you increase the temperature from 40 to 100 degrees Celsius, the drying rates are quite high, but it have negative impact on my lipid content. Along with drying of water, it has been taken out the main nutritional value that present in that biological product. So I have to get compromise, whether I have to make the reaction much more faster or whether I have to make the process much more slower without losing my actual product. Okay, so that is where we are going to get trade-off. So in case of increasing the temperature, the lipid content is increasing and then it's got decreased. That means like by making the process much more faster without getting compromised in the time factor, we are losing out the main products. Okay, so this is how like we could able to get where I have to choose which temperature might be much better without compromising on the quality of the product. So this one is for convective heating, and this one for microwave heating. So whatever way that we could able to get in case of convective heating, that can be attained much better quality in case of convective heating. Like if the increase in lipid content was relatively little high, okay, but still whether that have they're playing a significant role or not, that and all we have to statistically evaluate. At the end, we can learn that the overall yield is somewhat far better than a convective heating. And apart from that, it is going to contribute in terms of energy consumption. Okay, minimize energy consumption. Apart from that, it is going to contribute for the protection of environment. The amount of energy that's going to spend to dry through convective will be much more higher than the microwave drying. So these are the some of the aspects that made that okay, this particular microwave drying can be much more efficient when compared to the convective drying, which the quality of the product has been verified through FTIR spectroscopy also. Okay, through which we could able to learn that the overall idea is like this microwave drying have much lesser environmental as well as economical impacts compared to the convective drying. So these are the work has been published in Bioresearch Technology Journal in 2021. This is one such case study which give you idea like for drying a biological product, how we could able to choose the best technique. Okay, it shouldn't be focused only on the decline in moisture content. Rather, apart from that, we have to even take into the consideration of economical aspect, environmental aspect, as well as societal aspects. So that is how like you could able to attain the goals of triple bottom line to attain sustainable development. So apart from this, we have been working on pyrolysis. Okay, like anyhow, this might be little far away from the processing of food products. Okay, because till that point of time, you will be very much interested in working at very low temperature regime. Okay, because your overall aim will be just removal of water, nothing more than that, right? But right now, with that background information, we have utilized the same microwave assisted technique for pyrolysis. Pyro means heat, lysis means breakdown. So we are trying to break down the materials with the help of heat. Okay, so in that I'm going to explain two more case studies. One is all about machine learning prediction, how we could able to use the today emerging technique in case of data or information communication technology altogether, machine learning algorithms, how we could able to utilize machine learning algorithms to predict the biochar yield. Okay, this is all about the computational aspects. Then I will be explaining one more case study on like what are the different factors that influence the microwave assisted pyrolysis of sugarcane bagasse. Okay, so these are the two case studies we are going to see further. Like as I mentioned, like while you go for pyrolysis, okay, while you try to break down a material, okay, which would able to release three different components in three different states. For example, the final end product may be in solid, in liquid, or in gas. Okay, like under which conditions we are going to do this pyrolysis process. Based on that, the composition of the product that we are getting might be little different. Okay, like in case of any agro residues, while you go for pyrolysis, okay, especially at higher temperature, say around 500 degrees Celsius or 600 degrees Celsius, which in fact we are not going to work for drying out. Drying we usually deal at around 100 or 120 degrees Celsius, not more than that, right? So this will be on little other end with higher temperature, where we are trying to break down the overall material itself. It might landed up in producing a solid product called char, or whatever the gases that coming out that can be collected and that can be used for producing alternative fuels, syngas. Okay, that is also possible. Or even if our agro residues have some oil content, even that can be also be collected through gases and condensed further to get the oil. So like that, from any agro residues, we could able to get any of these three products. Okay, so we have to choose our technique in the right manner to maximize the desired quantity of our product. So if you are really looking for solid biochar or liquid bio oil or gaseous syngas, based on that we have to check out our experimental conditions so that we could able to get the product much more better manner. So what we are trying to do is like we are trying to understand what are the key factors that would influence this micro-assisted pyrolysis technique through machine learning algorithm. So here we have taken into the consideration of volatile matter, carbon, ash content. These are all being called as proximate analysis. Or if you are going for elemental analysis, every biomass, okay, is made up of carbon, hydrogen, nitrogen, sulfur. So those kind of elemental level composition that might also influence your final quality of the product. Apart from that, these are considered as operational parameters. How much initial amount of solid biomass that you have taken, how much time it is going to get exposed to the microwave radiation, how much power intensity that we have been kept in the system to speed up the process. Are we having any additional absorbers? Because in case of direct heating, we learned that like without the help of the absorbers, the heat wouldn't be able to travel. So whether people have worked out in addition of any other additional observers or not. So all these factors we are trying to take as a key input parameters as an input, so that we are trying to train our machine learning models to understand the correlation between these 11 input parameters with our output. Output is we have two. One is all about the yield of biochar, the yield of solid material that we are going to get out of this microwave assisted pyrolysis process, and then we are trying to understand its heat content value. Okay, because like we are trying to utilize this biochar as a source of energy. Okay, so how this model can be utilized further to correlate the relationship between the input and output parameters. That is what we are trying to do. Like if you go with any machine learning algorithms, there will be two things. One is all about training the model first. Once it has been trained, you have to test it. Okay, for the same data set. Even we can go further validation of those trained model conditions in our laboratory condition also. That is being called as experimental validation. So it is need not to be always a pure computational work, rather it can be a combination of computational work as well as your laboratory experimental work. So here we have used several key parameters to find out the relevant data from the published literature, and that's how like we have created our own data sets with reference to all these 11 input conditions and 2 output conditions. So we have created a complete data set of 240 rows which have all these 13 columns. Okay, so 13 column of matrix has been created. These data sets have been cited from the published literature, and we have been tried several machine learning algorithms such as multiple linear regression, string gradient boosting, random forest, support vector machine. So these are all some of the machine learning algorithms that is being used. Still few more are also available. Like each and every algorithm uses a particular technique to try to understand its correlation between input and output parameters. So we are trying to find out among these several machine learning algorithms which model would be able to better explain our experimental data set. Okay, which other data sets have been published by various researchers across the globe in various period of time in the last 10 or 20 years. So the data will be normalized, and that is how like we could able to get the overall idea like how this particular yield of biochar can be further maximized, which is well beyond the capacity of human to check it out manually. So that's why we are taking the help of machine to read it, learn it, and then tell us which one might be much better. So among the input parameters, like what is the variation, what is the standard, all those things have been clearly analyzed, and then we are trying to give the input features to the machine learning model so that we could able to get the overall idea about the correlation between input and output. This particular column is called as Pearson correlation coefficient or Pearson correlation matrix. This will give you a clear-cut idea about the link between your input and output. For example, volatile, okay, and how it is being linked with fixed carbon, and then volatile, how it is being linked with ash, and then likewise we could able to check with this yield factor also, because that is what the final output. The rest are all input. So by reading just this one image, we could able to know whether how all of these input parameters is being linked with your output, whether it is in a positive correlation or in a negative correlation, just by looking at the value of whether it is having plus or minus. And then based on the value it have, how much impact it's going to have on the output of your yield. Because at the end of the day, we are trying to maximize our yield. So how we could able to enhance the yield? What are the factors that influence? Right now, I have taken into consideration of 11 parameters. So among these 11 parameters, which are the factors which is going to influence my yield very effectively, or where I have correlation matrix? One left hand side is given for yield and the right hand side is given for higher heat content. So my focus is on the overall yield, or my focus is on the higher heat content. I have to vary my experimental conditions over here. So once it is being understood, then we are trying to train the model for different algorithms. Okay, like one is extreme gradient boosting, random forest, support vector machines, and linear regression. So among these models, okay, like which one have the higher R-square value correlation coefficient, and which one have lowest root mean square error, which could be able to explain the data set much more effective manner. So that is how we learned that among these models, this SDB model has been found to be much more best fit for the given data set. So you could able to explain the experimental observations in a right manner. So we are trying to understand among those 11 input parameters, which one was the very key influencing factor for getting the maximized yield of biochar. It is all about power. So power intensity that you set in microwave, how much intensity that you give, that is what going to dictate the overall yield of char in a very higher ratio. Then it's all about the concentration of absorber, whether water is present in the system or not, because that is what going to dictate whether the heat can be conducted further or not in case of microwave drying or diuretic drying. So how much time you are going to play. So we realize that apart from your biochemical characteristics of your biomass, it's all about the main operational parameters of drying. That is what going to dictate the overall yield. Okay, so this kind of analysis we can able to carry forward, and we could able to learn like whether we have to focus on the characteristic nature of biomass, or whether we have to focus on our operational conditions, so that we could able to maximize the desired product attribute. Okay, so that is what we were able to know out of here. And input features. Okay, like in case of higher heat content, which are the factors that are going to influence all those information we could able to get. And when compared to any other technique, this microwave assisted technique, we could able to get more higher heat content value at low temperature itself. So that is one great advantage that we used to have. Even that we could able to get out of this particular observation. So these data sets can be visualized under different conditions. Okay, to check out whether it should be at low or high, how it is going to influence all those observations we could able to make by having these kind of diagrams. Okay, whether it will be having any trends, okay, whether it will be increasing or it will be linear, then it will be independent of concentration, like all those information we could able to get out of this kind of plots, so that we could able to get the overall idea. Okay, what might be the very optimal environmental conditions through which we could able to get the desired product. Like for example, we are learning that the carbon content should be always more than 50%, which could able to enhance the biochar yield, and power should be always in the range of 400 watt to 600 watt. Like we could able to get the overall idea under which conditions we have to work on, so that we could able to maximize our product. So the conclusion is, yeah, this is the last slide. This could able to explain like among these several parameters. Okay, like suppose if the power with blue color, that means it have low, then it is going to negatively impact your yield. That means more amount of power would able to positively enhance the yield of char. Likewise, that is a very key parameter that's going to dictate your char yield. Then comes nitrogen, oxygen, volatile. Like that, each and every parameter, whether it is low or high, based on that, we would able to check whether it would able to offer positive benefits or negative benefits. This is we have done for both char as well as for higher heat content value. Okay, so like that, we could able to get the overall idea of what are the factors that definitely influence your desired output and what should be the optimal range. Like as I mentioned, among the 100% of the data set that you have, first you will be train the mathematical models through machine learning algorithm with 70% data set. So the remaining 30% data set will be tested further, so that you could able to understand whether the model has been actually trained or not. Like in classes, we used to have teaching, right, for some 25 hours or 30 hours. Then after that, we will be having 1 or 2 hour exam. So the first phase is all about training. Okay. Then once the training is done, then we will be checking it out, right, whether it is being learned or not. That is what all about testing. So the same thing here is also being followed. So we could able to train the model in the right manner so that it can be tested later. Even apart from that computational testing, we can take it further to the lab for real-time experimental testing also, experimental validation also can be possible. So that is how like we could able to check like how the biomass composition as well as the microwave conditions is going to influence your output. Okay, through a machine learning algorithm, that is also can be possible. So this is the end of the second case study. Then let us go to the experimental part once again. Like now, among those 11 factors, which are the factors that significantly influencing your yield that we observed, that we are trying to check out experiment at the lab. Okay, so here we have been taken sugarcane baggage. Overall aim is to convert the sugarcane baggage into biochar in microwave. So these are the different characteristics. Okay, these are the different key factors that is going to study over here. For example, feedstock amount. Okay, how much amount of biomass that we have taken, whether it have any role in dictating the overall yield of char that we are going to study. And then second point is all about particle size. Okay, whether the size of the particle is going to play any role in dictating the overall yield of char. Catalyst dosage, microwave power, how much time it's going to get exposed, what is the overall moisture content that present in the system. Okay, whether all these factors are going to influence my input to output. Okay, so that is what we are going to study experimentally. Okay, for this also we have done like optimization through fractional screening designs. Okay, so the experimental variables have been selected based on the previously published literature, and then the range of parameters was even selected based on the preliminary trials. Then these data has been fed into the design expert software to get the wide range of conditions. Because like in the moment we talk about optimization, there are two different approaches. One is all about one variable at a time approach. Another one is response surface methodology technique. So in case of one variable at a time approach, sometimes we might miss out the global maxima. Rather, we might land up in local maxima, which we decide that this will be the maximum that we could able to attain. But the moment we take the help of design of experiments, even we could able to make ensure that we have reached the global maxima. So that is a point of doing this particular study. So here we have been varied feedstock amount, feedstock type, moisture content, dosage, power, and then reaction time over a range. Okay, so just we are talking about low value as well as high value. Okay, instead of these two factors, suppose we can go for three factors, like one is low, one is medium, another one is high. Like that way we can make. Otherwise, we can make 5 values: extremely low, low, medium, high, extremely high. But the point is, like the more you make, the system will become much more complex. Okay, like for example, 4 to power 2, 16, but 4 to power 3, 64. Okay, 4 to power 5, much more higher, right? So that is how the number of experiments will be made much more complex. So just to make it simple, we have just taken only low, medium, only two levels. Okay, instead of that, if we consider 3 levels or 5 levels, then the number of experiments will be much more higher. But still, the point is like we could able to utilize this kind of modern analytical tools, softwares to make our process much more simple. So by carrying out the list of experiments, like we learned that like what are the factors that is going to influence the yield of char. Like for example, among these factors, whichever is lying on the line, okay, which are going to significantly influence the yield. Like which is lying on this line, which is not going to influence the yield. Like for example, moisture content, that is not going to influence that much. Rather, the rest of the other 5 parameters are going to influence the char yield much better manner. So through this half normal probability plot as well as the Pareto chart, we could able to get which are the factors has to be further taken into the consideration. So initially we have taken with 6 variables, 6 factors, and in that 6 out of 5 is going to play a significant role in dictating the yield of char. Okay, so that is what we learned out of these 2 plots. Then for further study, we have taken into consideration of those 5 variables for further. Like the model has given us, we have to carry forward 32 set of experiments. For example, like in this case of feedstock amount, we varied the concentration from 2 to 10 grams. In feedstock size, 1.5 to 0.015 centimeter. In case of moisture content, it is varying from 8 to 16%. In case of catalyst dose, 10 to 30%. In case of power watt, 362 count 20 watt. In case of time, 5 to 20 minutes. So these are all 6 input parameters that we have given over a range, just as low as well as high. So the model has given that we had to carry forward 32 run-up experiments. Okay, so that we could able to experimentally check out under these varying conditions, what is the yield of char that we are getting. Once that is being done, the same thing has been fed into the design expert software, so that here also the model will be learned further to predict, okay, which could able to almost as closest to our experimental conditions. So that is how like even the modern sophisticated tools such as design expert would able to help us in understanding the relationship between the different variables over a range of conditions with our experimental observation, so that it would able to tell us like what kind of situations can be maximize our yield. So you can see that the maximum and minimum biochar yield has been happened in run 8 and 22. For example, run 8, under these conditions, we have got the maximized char yield of 44%. Under in conditions of experiment number 22, we got the very minimal char yield. Okay, so by this, we could able to get what permutation combination of this working variable could able to maximize your yield. That we could able to get out of this particular trial. Okay, otherwise, if you are going to do the same thing just by trial and error with the normal optimization technique, it will take so much of time as well as resources. So that is why like we are very much interested in understanding through a modern mathematical models stuff. We could able to get the overall idea. Even we could able to come up with a simple equation. Okay, suppose for example, A is your moisture content, B is your factor. A is feedstock amount, B is feedstock size, moisture, dose, power, and time. So which are the one positively influence your yield? Which are the one which have negative impact on your yield? All those things we could able to get just by observing whether it have positive symbol or negative symbol. Then apart from that, how much it will impact. So that you could able to understand by the coefficient, whether it is 7, 4, 0.2. Based on that, even you could able to know like how impact it will be. So all those information we could able to get. So that is how like we could able to come up with a generalized mathematical expressions to explain our experimental observations. So that has been further statistically verified, and we are trying to understand like what is the individual effect of those parameters. Apart from that, what interactive effect it will be having, because like we are seeing all these 6 variables as a individual. Okay, but we are trying to we are forgetting that like even these individual parameters have some interactive effect on other parameters. For example, if I increase the power, okay, we are focusing only on how power will helpful in drying. Okay, but by increasing the power, it might be having some impact on time factor. It will be having some impact on the other factor also. So what is the interaction between a variable A as well as the variable B, C, D, E, F? Even that interaction effect also we could able to check out over here. So all this information good able to help you to understand, okay, like what is the range of product that we could able to get, whether it will be having the desired attributes or not. All those information we could able to get, and that has been experimentally verified through other sophisticated analysis, like passing through scanning electron microscopy or FTIR spectroscopy or like EDS spectrum. We are trying to just confirm, okay, whether whatever the model conditions that have been mentioned, are we getting a good quality of the yield or not? So that is what has been done. That is what been observed. So just to conclude, the take-home message, like among the drying techniques, microwave drying technique also have a huge potential to make it in a real-time applications. Like it have very less effective time, especially for volumetric heat generation as well as for mass transport. Like we can make use of microwave heating, which have several advantages over traditional technologies. And even we can trying to utilize modern techniques such as machine learning algorithms or like design of experiments to get the real-time optimized environmental conditions, so that we could able to make the process much more economical. Okay, much more technically feasible, much more socially acceptable. So apart from that, like we do work on other some of the products, okay, like kombucha, SCOBY, Astruvite, beverage, some char, some other hydroponic systems. Okay, and thanks to our funding agencies, like we could able to establish some of the facilities in the lab. And thank you once again for this opportunity. If you have any questions, I am very much happy to.
It was really informative. Thank you. Thank you, sir, for enlightening us on the mechanism and process kinetics of microwave-assisted drying and as well as pyrolysis. I hope all the participants joined through both online and offline modes have not failed out from it. If anyone having question, you may ask to speaker by raising hand, or may you may write question on the chat box. Professor will be here to answer. Offline, we doubts.
Hello, sir. This is Jnanamurthy Ishwaran from IIT Kharagpur. Sir, actually, I am working with some startups. We are facing some real-time problems with this spirulina. So, my colleague, we are having two products. One is like NutriBar, where we have to add this spirulina, dry spirulina, but because of its taste and aroma, so it is, we are like compulsory to reduce the concentration of the addition of the spirulina, or we have to increase the percentage of sugar in order to mimic that taste, and then in order to overcome that taste. One more problem is we are also using this spirulina for colorant. So this colorant is where we are trying to use it for hydrothermal treatment of this peas, beans. So vegetables, then we go for drying, where this vegetables or green grams will go for like ready to cook products. So there the problem is the lipid content of the drying spiral. So how to overcome this? So it is
Like as I mentioned, we do have several types of drying. Okay, but where we are going to get compromise? Are we going to get compromise on the cost factor, a time factor, or the quality of the product that we are looking for? That is where we have to choose the best available technology. Okay, like if you are saying that you would like to dry the spirulina species, okay, but without losing its aroma. Okay.
No, sir, we don't want that aroma.
Okay, you don't want to have that aroma. Okay, but it has to have that
Colors.
colors.
Product quality should be there.
Okay.
When we go for Nutripar, we want that lipid content.
Okay.
When we go for colorant, we don't want that.
So we have to work out on these techniques. Okay, like you can choose any of these techniques among the several drying techniques. Like for example, you would like to maintain that nutritional value. Then most of the time people are going for freeze drying. Okay, the reason is it is that technique is especially meant for very sensitive products. Okay, so if you don't want to lose that value, okay, the moment you dry it, you are rising up the heat. Proteins will get denatured at higher temperature. Okay, so if you don't want to denature it, if you want to retain that product, you retain the attribute of that product, then we can go for that kind of freeze drying. But the point is, energy intensive process, it will be quite time consuming. So, like whether you want to remove the odor or whether you want to retain the odor, based on that, we have to try out like what are the different techniques available under experimental conditions in lab. Then we could be able to figure it out. Like especially if you want to retain the nutritional value, you can go for these kind of freeze techniques. Suppose if you are not really concerned about the odor, just you want to keep the color alone, then for that we can go for microwave based drying under optimal conditions. We could be able to do. So likewise, we could be able to either increase or decrease or maintain the desired attribute of the product.
Right now, we are using like heat pump dryer for the drying of spirulina to use it in this Nutripar. But now it is like you have given some idea like microwave is reducing the lipid content. So,
like microwave at which power intensity? How long? That is what I'm saying. Like it's not all about only one parameter. Like suppose if my concern is only removal of moisture, I need not to focus on anything else. Then you can simply raise up the temperature. Within no time, you could be able to dry out the product. But you would like to dry out the product without losing the attribute of product quality, such as taste or aroma or some nutrient value. Then you have to work out and you have to compromise on a certain factors.
For colorant, we think we can adapt microwave.
Yeah,
because we don't need much nutrients.
Yeah, there your just idea is it should not be get more dark. It should be green in nature. Okay, fine. For that, under which experimental conditions it can be attained. That we have to optimize. Then we could be able to move forward.
Thank you, sir.
Yes.
Hello, sir. Good morning. So you have said the observer will be used during the biodiversity. So the purpose of using observer is to increase the absorption rate of microwave energy. But microwave energy can be absorbed if the water is present in the material.
Yeah.
So what is the purpose of using observer again?
To intensify the process, nothing more than that.
Okay, sir. So can we use it during the drying process also?
Yeah.
Will it
But it shouldn't have impact on your product quality.
yes, sir. Will it affect the quality?
That we have to work out. Like for example, by default, water itself is absorbed.
Yes, sir.
Okay. Suppose if there is no sufficient amount of absorber present, you can re-add water itself, or we can re-add any other component.
So what is the other observer?
Like in our case, just we will add a bit of char in the earlier stage itself,
Okay.
because that itself would be able to conduct the heat.
Okay.
So we are trying to make char at the end. We are adding char also at the start, so that our process time will get reduced. It is not contaminating, because we are also looking for char only. At the end, start itself, I am adding a char also. So finally, the yield what I am getting, that process can be made time less.
Okay, sir.
Suppose if I am adding something else as a seeding material, okay, as a observer, then it might not, it shouldn't affect my quality of the product. Only that should be the concern. Like in household, if you would like to recook the food, people used to add a water, right? If it is not having, we have to add a bit so that we the process much more effective.
In slide number 50, can you explain the interpretation?
Yeah,
Just I want to know.
yeah, sure.
Slide number 50.
Very good. Yeah.
Can we explain how we can interpret?
Like for example, yield, right? Like in childhood, you might have seen there are certain places A to B. What is the distance between that? For example, from Rourkela to Bhubaneswar, 330 kilometers. Rourkela to Kharagpur, 200 kilometers. Rourkela to Kolkata, 450 kilometers. You make a matrix, then we could be able to say, right, from point A to point B, what is the distance? The same kind of thing. Like you forget about the other portion. You bisect like this. Okay, so you just try to understand, like these are all input parameters. The yield is the final output parameter. So volatile, it's contributing 0.2 for the yield. Observer 0.5. Ash content, it's in negative value, minus 0.3. Okay, then carbon 0.2. Hydrogen 0.09. Nitrogen 0.2. So through this, we could able to understand like what is the role of volatile in dictating the yield of chart, whether it have positive impact or negative impact, based on just understanding whether it is a positive value or negative value. And then second point is like how much value is there. That would able to tell you whether how impactful it will be. The first one is all about just a kind of qualitative analysis. Yes, no. The second one is all about if yes, how much? If no, how much? So that we could able to get. So that is how, like based on the data set that we have developed, this is called a Pearson correlation matrix. Just try to understand the relationship between a several input variables to a one output variable. Like we are writing equation, right? Y is equal to mx plus b. So instead of x, if it's having x1, x2, x3, x4, x5, then we are writing equation y is equal to mx1 plus mx2 minus mx3 minus mx4. That means x1 and x2 are positively influencing your y, but x3 and x4 are negatively influencing your y. And then the value of m of each x1, x2, x3, x4 represents how much impact it will be.
Sir, in our zone, we'll get the final equation with that. It is kind of prediction.
Yeah.
In the other part, there is a machine learning. That is also kind of prediction.
Yeah.
So what is the difference between this and this?
Yeah, that's one more interesting question. Like in case of RSM, we have both experimental observations. What we are trying to do is like we don't know like what type of experimental conditions we have to work on. So we have been given the machine, okay, the RSM thing, a range of variables. For example, I would like to work on power intensity 400 to 600 watts. I would like to find out under which conditions I could able to maximize my yield. So I will just inform that 400, 600 watt. That's it. Like this, whatever the variables are there that I am loading into the design expert software, so that it will based on the number of variables that you have, based on the number of levels that you have. As I mentioned, it may be 4 square or 4 cube or 4 to power 5 experiments based on the level low, medium or low, medium, high or extremely low, low, medium, extremely high, like that. It may come up with any number of experiments that will be dictated by software. Those experiments we are going to carry out in the lab to understand what is being happening. That data we are loading into the software. After that, only the machine is learning.
So based on the RSM software, we are going for
experiments, and then those experimental data.
RSM, I know. So based on the experiment, we will get some prediction the equation.
Yeah.
So the other side is
machine learning. In that, first thing is like machine itself will learn. Okay, even we need not to give any experimental data from our own lab. Okay, like based on the publishing literature, many people have already carried out some experiments. They might have told that under this condition, this is what they got. This is what they got, like that. So those conditions we are loading into the machine learning algorithm to understand what is the relation between input and output.
So based on the previous literature, we'll give some input to the machine learning software, we'll get some
prediction. That might be, if we have done the training and testing in the right manner, that itself might be working fine. But whether it is working really fine or not, that also we can able to experimentally validate in our lab. In case of RSM,
so in the machine learning, it's completely eliminating the
experimental part itself. Yeah,
stage.
yeah. And in case of experiment, you can carry out 50 times, 100 times in your lab, not more than that over a period of time. But in case of machine learning, when it is needed, is like if the system is really robust, okay, it can able to work on any range, any condition, or like it might be working in IIT, it might not be working in NIT, something like that if you want to say, or under which condition it will be working. Like it can able to normalize the overall generalized data sets. Like that way, when you have the more exhaustive list of data sets, we can go for machine learning algorithms.
So compared to machine learning and the RSM, if we compare the output of those two, what will be the maximum probability of error?
Like in case of RSM, we have carried out the experiments. Based on that only we have done the optimization.
Okay.
But in case of machine learning, the data sets has been collected from several places. Okay, around the globe. It might be having wide variation also, but everything will be normalized and it will be giving you a very generalized experimental conditions over there.
Okay, thank you.
Yeah. Okay. Okay. Okay, in the problem of non-uniformity in the microwave heating, how can we minimize this? Okay, like it is all about the deviation from ideality and reality. Okay, like in real time, it will be having non-uniform in nature, but in order to make the process much more simple, our comprehension much more easy, like we are trying to generalize. So that is why, like non-uniformity, we are trying to address with that would be able to sort it out. How can we control drain rates in microwave as it is possible in conventional techniques? Just by varying the external conditions, like how much power you would like to keep or how long it has to get exposed. Based on that only you would able to vary the heating rates. Like not only on power, time, okay, how much samples that you have loaded, like all these factors can be able to influence your heating rate. Okay, third one is microwave heating happens from inside out, but Marshall losses happen from the surface only. It need not to be Marshall losses need not to happen not only from the surface, it can be from throughout the stuff. Okay. You talk about the prediction of microwave processing yield in a process which is so non-uniform as microwave heating. How far we can trust the mathematical models of the prediction? Like even in case of microwave heating also, we have done the experimental observations. Okay, like how fast it's happening. That is what we are trying to explain with the mathematical models. Okay, so based on the correlation coefficient R square value and the root mean square error, we could be able to understand the adequacy of fitness of those mathematical models. And ultimately, at the end of the day, like what is the experimental observation that we had and how much can be explained through mathematical model? That is what we are trying to check out. So just by understanding the correlation coefficient, say R square and root mean square error, we can check out whether the model that could be able to explain the experimental observations in an adequate manner or not. So does there any formation of degraded products in the biochar when processed with microwave, which ultimately affected its quality? Yeah, like suppose if you have overheated the product, instead of making it into char, it might get converted into ash. Okay, that depends on the availability of organic as well as inorganic content in the biomass. So even that also can have role on deciding the quality of the biochar. So it's all about optimizing the right environmental conditions. Okay. There is a concept of MW power density in the MW drying. How come the use of direct power values like 860 watt is justifiable? Okay. So unlike in convective heating, where we could able to vary the temperature, we could able to vary the time. Here in case of microwave drying, we don't have that kind of direct control. Rather, it will be in terms of watts only. But how far you are exposing the substrate for microwave, based on that you could be able to correlate whether it will be helpful in drying out the product or not. All those things. That's the basic way people try to work out. Like even in case of industrial drying also, people are working on 1 magnetron, 2 magnetron, like that only. So it will be always in terms of power intensity in case of microwave drying, unlike in convective heating. Right. Okay. So what are the products we can dry using microwave freeze drying? Okay. Microwave freeze drying or microwave drying? Microwave drying. Okay. Huh? Any heat sensitive product. Either it may be freeze drying or microwave drying, right? Microwave freeze drying. Microwave assisted freeze drying. Okay. Fine. So especially for heat label compounds. Okay, heat sensitive compounds. Good.
Thank you.
Thank you. Thank you again for this opportunity.
Now, the question and session. Thank you, sir, for informative lecture. Now, I would like to request Dr. Rachna ma'am to present Professor Valla Subramaniam with a memorandum as a symbol of gratitude. Now we will take a short tea break. Our next lecture will be started at 11:45 a.m. I request all the online participants to kindly join the Zoom meeting before 5 minutes. Also, I request all the offline participants to be present by 11:40 a.m. Thank you.
Now we are going to start our second lecture of today's morning session. Next, I call upon Dr. Preetham Sarkar, an assistant professor at the Department of Food Process Engineering, NIT Rourkela. He graduated with an MS in Food and Nutritional Science from California State University and PhD in Food Science from Purdue University. Thereafter, he has been working as an assistant professor of food science at National Institute of Technology, Rourkela. Dr. Sarkar's primary research interests lie in the development of delivery vehicles for protection of functional molecules within food systems, including bioactive food packaging. He has published 43 articles so far in the international journals and few book chapters. Dr. Sarkar has received extramural funding from SOP and DST in the area of delivery system and bioactive packaging. Thank you, sir, for being here. I would like to request to deliver your lecture about sustainable biomaterials from agricultural bioproducts and their application in food packaging. Over to you, sir.
Thank you. Thank you, Adrian. Thank you, all of you, for giving us this opportunity. So today's talk will be sustainable biomaterials from agricultural byproducts and their application in food packaging. So today's contents will be introduction to food packaging. Will briefly introduce what is food packaging. Maybe all of you know that. Then specifically focus on active packaging and coatings, the type of active packaging systems, and with a more focus on antimicrobial packaging and coating systems. And then we'll talk about two case studies from our lab, focusing on developing packaging materials from ag byproducts, which is the jackfruit seed starch and tamarind kernels. So the focus of our lab is the core is something what we call as a food material science. So we want to, at one end we have emulsion-based, we study emulsion-based delivery systems. We study edible films and coatings, and also to some extent on gel-based delivery systems. Okay, so to study all these systems in food, the materials are we have to study food and food materials from a material science standpoint. So material science is at the core focus of our lab. So if we talk about this packaging, and if you just go to Google and give a search, you'll find a lot of articles, and especially organizations like National Geographic. You find a lot of articles coming up in the last few years, especially this National Geographic magazine, like plastic food packaging was one of the most common beach trash in 2018. That is one, and another one was in another one came out in California. There is this sweeping new plastics. Okay, could be a new game. So everyone wants to get rid of the synthetic plastics. Okay, so that is a big problem overall in the globe. In India also, there are a lot of issues like food packaging forum. They are saying that India plans to ban or single-use plastic items. And so there are a lot of articles regarding this if you just do a Google search. So that is one. So environmental safety is one concern. We want to make the environment safe. And second one is, of course, we have a food safety concern, because of course foods are very delicate systems, and therefore they will be attacked by a lot of different classes of microbes, starting from bacteria to viruses. So therefore, of course, if you have a little bit of microbiology background, you will know that these are some of the common bacteria and viruses and parasites which will attack the foods, and therefore we need to develop preservation strategies to make the food safe. So if you want to make the food safe, of course, we have a lot of other techniques like pasteurization, ultra high temperature, sterilization, high pressure processing, microwave processing, so many pulsed electric fields, so many new technologies have come up. But one problem with those techniques is the high cost. It's very high cost. So if you want to approach a small scale farmer, may not have the potential to buy such a big equipment for primary processing of your crops. Okay, so therefore, so the major problem is the cost and also the maintenance cost. So there's so much of money that is required to maintain those equipments. So therefore, if you want to give an alternative strategy, so the antimicrobial food packaging can be one of the important alternative strategies to improve food safety as well as environmental safety. Okay, so active packaging is defined as a packaging system that deliberately incorporates different components, mostly active compounds, which are bioactive compounds, antimicrobials, antioxidants, which can be embedded within the polymer, and it can be released into the package, to the food system, to the food surface, or into the core of the food. Okay, active packaging changes the condition of the packaged food to extend the shelf life. So overall goal is you want to extend the shelf life via different strategies, including active packaging. So just to give you an idea, if you see, there's a number of documents that are published in the last few years. A lot of top journals, they are all publishing in this particular area. But just to give you an idea of what is happening in the publication stand from the last few years. So active, there's novel food packaging materials, active packaging if you want to develop. So there is, so you need to have 4 different properties. You need to have biodegradation property, you need to have active properties or bioactive properties. Need to have good barrier properties, and it can be best is if it is in the form of edible coatings. Okay, so you don't have to throw the material, you can eat the coating along with the food. That will be the best case scenario, but maybe that is not always possible because of different challenges. Okay, so but the best case scenario will be if we can develop edible coatings. Okay, coatings which are edible. So again, if you want to talk about these systems, like just to give you some news release, like institutes like MIT, they are working on systems to develop edible coatings, to develop the shelf life of banana, for example. Okay, so they are using different type of materials like this chitosan and pullalan and this type of things. Okay, and they want to preserve this banana kind of products. So that is one they are using. In this case, they're using nano silk. The silk is there's a very unique material which has good antimicrobial properties, and they can be used for extending the shelf life of banana, for example. Another thing is at Harvard University, they are also doing this type of work with pullalan kind of a polysaccharide, with thyme oil, lysine, and citric acid coatings. Okay, so this type of research in edible coatings and packaging is happening across the world, and so we need to also focus on that. So based on that, active packaging is a food condition in which it can control these different processes like physiological processes. It can control the chemical process like lipid oxidation, which is very important in food. Physical processes like scaling of bread, dehydration. Microbiological processes like spoilage, control the spoilage of microbes, and also infestation by insects. Okay, so if you in the food science field, of course, we need to protect our food. I mean, so many stress factors. So bioactive packaging can be a solution to all of these. Just to give you some examples of active packaging systems, okay, you can have oxygen absorbers, you can have carbon dioxide absorbers or emitters within the package, you can have ethylene absorbers, you can develop antimicrobial packaging. So antimicrobial packaging is the more major focus of our lab. Okay, so these type of materials are there, and then there is ethanol emitters. Okay, ethanol emitters can encapsulate ethanol type of compounds. Okay, then you have moisture absorbers. Okay. Then you have flavor or odor absorbers. Okay. Then you have self-heating and self-cooling packaging systems, and also packaging systems which can change the gas permeability of the material. Okay, depending on the conditions. Okay, so 9 or 10 different types of active bioactive packaging systems are available, and they can be developed. Okay, so out of all of that, our major focus is of course the antimicrobial. So antimicrobial food packaging acts to reduce and inhibit or retard the growth of microbes that may be present in the packed food or packaging material. So that can be done by different ways, like addition of sachets or bags containing volatile antimicrobial compounds. So you can add some sachet. So in the package, you can keep some sachet type kind of a product from which the antimicrobial will be released. First. Second, you can have incorporation of volatile and non-volatile antimicrobial compounds directly into the polymers. So you can entrap these type of active antimicrobial compounds within the polymeric matrix. Okay, that is what our lab more focuses on. Then coating of absorbing antimicrobial at the polymer surface. Okay, so at the polymer surface, not inside the core, but at the surface also, you can modify the surface of the polymer by absorbing different antimicrobials. The immobilization of the antimicrobials to polymers by ionic or covalent linkages, you can chemically react these antimicrobial compounds to the polymer, and you can develop new ionic or covalent bonds so that they can be more stable. And use of polymers that are inherently antimicrobial. Okay, so you can use biopolymers. Okay, so in this when I'm talking about polymers, So we are mostly talking about biopolymers. We are not talking about synthetic polymers. Synthetic polymers we want to get rid, right? Polymer means biopolymers, which is, and the core word over here is sustainable. The word is talking about sustainability, so sustainable polymers, okay, or green polymers. So polymers which are obtained from biological sources. So use of polymers that are inherently antimicrobial. So in food, we have one very good example, that is chitosan. Chitosan is a positively charged molecule, macromolecule, which has very good antimicrobial properties. So based on that, we'll talk about these different classes of sustainable polymers we have in food. Like we have so many types of starches: sago starch, rice starch, corn starch, potato starch, pea starch, lotus stem starch. So a lot of things, a lot of starches that are coming up. Then you have cellulose, you have modified cellulose, like methyl cellulose, hydroxypropyl cellulose, hydroxypropyl methyl cellulose. Also, there is microcrystalline cellulose. There are 6-7 types of cellulose are there. We are talking about with Professor Balasubramanian. There is bacterial cellulose. A lot of words are nowadays coming up with bacterial cellulose. And then you have chitosan, and then you have a whole world of gums and hydrocolloids. So different gums, guar gum arabic, gum tra, gum gatti, gum karaya, so many things. Okay, so there is endless amount of gums, okay, which are coming up. And within the class of proteins, which are sustainable polymers as proteins, we have caseins, proteins from milk, like caseins are whey proteins concentrate isolate. You have proteins from soy, like soy protein isolate. You have zein, the corn, the major protein in corn, the major protein in sorghum, another cereal grain, that is kefir. Then you have rice proteins like oryzanol, rice proteins. You have pea protein isolates, pea proteins, potato proteins. Okay, so many different examples are there which can be used in the packaging world. Okay? Now, if we talk about these materials, now we should also talk about byproducts. Okay, so we can also extract a lot of important compounds from agricultural byproducts. So that is one of the major current focus of our lab in the last few years. That is, we want to extrapolate or extract materials from ag byproducts, because ag byproducts they don't find much applications except that they are mostly used as animal feed or landfills and this type of thing. So they don't find much applications in the food industry. And so we want to make them more valuable. And one of the better ways is we can convert them into packaging materials. So I'm sorry for this slide. It showed good on my laptop, but it's not good here. But we'll talk about some materials like byproducts from fruits, like mango byproducts, pomegranate, grape, citrus, apples. This is berries. Okay, there is berries. Okay, then vegetables, mushroom, tomato, potato, carrot, so many things, eggplants, grains, legumes, and some miscellaneous like coffee byproducts. And we have a more focus on tamarind. India is the largest producer of tamarind in the world. So there's a lot of tamarind production in India, and we'll talk about those tamarind byproducts. Okay, so you can see that you have so many options and so many materials, and they need to be explored in terms of the packaging industry or packaging science. So we'll talk about two important class of molecules based on our case studies. We will talk about starch and we'll talk about xyloglucans. Okay, so maybe you all know the basic of starch. Starch is a hydrophilic biopolymer obtained from so many different types of plants. It is the major storage molecule, right? Plants store the excess carbohydrates in the form of starch. In plants, it has two different molecules, two different fractions: the linear fraction amylose and the branch fraction. Right, the branch fraction, this is a branch fraction, is amylopectin, and the linear fraction is amylose. The amylose is joined by alpha-1 4 bonds. This is joined by alpha-1 6 bonds. Again, so the branching pattern that is here, comprising of amylose and amylopectin for starch. Okay. So again, the arrangement, this is how the amylose and amylopectin molecules are arranged within the starch granules. There are short chains, there are long chains. Okay, and they are packed together in a highly crystalline order within the starch granules. So that is starch, and then we talk about the class that is xyloglucans. So starch, if you see the structure of starch, starch is known as a hyperbranched molecule. The structure of starch is hyperbranched or branch on branch. But xyloglucans is a class of molecules which are actually dendritic. The structure is dendritic. Okay, so there is a difference between hyperbranch versus dendritic. So dendritic means their chain length is much smaller. So if you see this, the chain length over here is you have to travel like 25 to 30 residues in the linear portion, and then there is a branching. So this is from here to here, there is like 25 to 30 residues of alpha D glucose, and then the branching starts. Okay, that is for starch. But for xylic glucan, we have to travel, that chain length is reduces to around 6 to 10. Okay, so this is much smaller over here. This is like here, 6 to 10. Okay, so therefore, the molecular density of starch is much lower as compared to your glycogen. This is xyloglucans. Okay, so therefore, the xyloglucans molecular density is much higher. We say the xyloglucan molecular density is higher, and therefore xyloglucans can also have good film forming properties. Okay, so both starch and xyloglucan have good film forming properties and can be explored. So xyloglucans is a polymer of, again, these are all big polymers. They have a molecular weight in the millions of grams per mole. Hence, mostly it's a polymer of glucose, xylose, and galactose. Okay, GLC glucose, XYL is xylose, and GAL is galactose. Okay. So with this background, we'll talk about the case studies to our latest work from jackfruit seed starch. So we wanted to see how whether starch and xyloglucans can be used in combination in the preparation of composite films. So we took just starch from jackfruit seed, because jackfruit seed, okay, some people eat jackfruit seed in this part of the world, but many outside India, there's no use of jackfruit seeds, and also many parts of India, there is no use of jackfruit seed. Okay, but I think in Odisha and Bengal, people eat jackfruit seed. That's there. But anyway, so we wanted to explore jackfruit seed starch and the xyloglucans from tamarind kernel, and we wanted to prepare this nanocomposite films from using zinc oxide nanoparticles. And they study on the shelf life extension of tomato. So this is our graphical abstract that we prepared. So we have jackfruit seed, and then tamarind kernels, and it is the starch. We extract the starch from jackfruit seed, xyloglucan from tamarind kernels. We use a plasticizer, which is glycerol, and we have zinc oxide nanoparticles. We select zinc oxide nanoparticles because zinc oxide is, first of all, it is US FDA approved material. Okay, it has a generally recognized as a BRAS status first, and second, it also has native antimicrobial activity. Okay, so therefore, because we wanted to prepare which has antimicrobial films, so therefore we selected zinc oxide. So we prepared the nanocomposite films, and then from the film, we went for basic characterizations. And using the film forming dispersions, we coated our tomatoes. We took tomato because tomato is very much delicate in terms of shelf life. It is not shelf stable at all, so very high moisture content. And we wanted to study the effect of this coating of tomatoes. So initially we did the raw material characterization. We did our SEM, scanning electron microscopy of our jackfruit seed starch and this tamarind xyloglucans, and then the XRD profiles. Okay, you can see the peaks at around 20 degrees, mostly 20 and 25 degrees. And for xyloglucan, the major peak was at around 20 to 23 degrees. Then we did some initial rheological characterization of these film forming dispersions. We had 6 film forming dispersions. We had jackfruit seed starch alone dispersion, xyloglucan alone dispersion, then a 1:1 ratio of jackfruit seed starch to xyloglucan dispersion. And then we added to this composition, we added zinc oxide nanoparticles, 1%, 3%, and 5%. Okay, so we had 6 dispersions. So we plotted apparent viscosity versus shear rate, shear stress versus shear rate, and then the G prime and G double prime. Okay, so you can see, of course, there is some linear pattern over here, and for the 6 films, and your JSS was lowest as compared to this one. XG was the highest. Both over here, JSS alone was the lowest, but XG alone was the highest, which we will also see in the mechanical properties. Okay, so these were the pictographs of the prepared films. We have the JSS alone, XG alone, the composite of JSS XG, and then we have the zinc oxide, because zinc oxide will give this whitish tinge. So you have 1%, 3%, 5%. Then we characterize the thickness. Okay, thickness ranges from 0.119 millimeter, this is millimeter, to around 0.133 millimeters. The moisture content, it reduced because 20.46 to 18.12 zinc oxide is kind of hydrophobic. Then you have water solubility. It also reduced from 48% to 42%. All I'm saying is compared to the controls, okay, JSS. And then the contact angle, because zinc oxide is again hydrophobic, it increased. So you can see 58, 74 to 72, and then it increased to 75. So there is not much of a difference between XG alone films and the zinc oxide highest. And 3 was at 78. Okay, so 3 was the highest. Okay, so 74 to 78. So, but still there was not much of a difference. Okay, and then this is 72 to 78. Then we have the color values, color values, the total color change, and this transparency values at 280 and 660. Then we did the microscopy, microstructure using scanning electron microscopy. This is our plain JSS film. Mostly it is this uniform. Okay, little bit of aggregates. Again, you have XG films. There's a lot of some more aggregates over here because of XG. The particle size of XG is large, and therefore you can observe some of these molecular aggregates. Then you have JSS XG combination, and then you can see the zinc oxide nanoparticles. Okay, 1%, 3%, 5%. And then we characterized at the molecular level. We wanted to study the FTIR studies. Okay, so FTIR profiles were almost similar for all the 6 films. Then you have XRD profiles. XRD, once we have the zinc oxide, you can see the sharp peaks. Okay, for zinc oxide nanoparticles. And then these were the DSC profiles. Okay. And we also wanted to study the mechanical, because whenever you are preparing the packaging material, the 2 most important parameters we must study is the mechanical property and the barrier properties. Okay, so these 2 are very important. So therefore, for instance of the tensile strength, you also see this JSS alone, it was like only 8 megapascal. But when what we found was when we changed that to XG, xyloglucans, it increased to 26 megapascal, almost a 3 times jump. Okay, and but when the composite it is around 15, and zinc oxide alone also could not increase the tensile strength to the level of XG. So even though we were playing with, of course, because we wanted to add antimicrobial function, we have to add zinc oxide. So the zinc oxide nanoparticle 3 had the highest tensile strength in terms of these 3, which is 20.65. But one of the major findings was XG films alone was also being pretty good in terms of mechanical properties. And if you observe the film also, it shows very good mechanical properties. And then we get this is elongation at break in percentages. It is almost 36% over in XG and 38% for zinc oxide nanoparticle 3. Okay, so our nanoparticle 3% was one of the best. Then this Young's modulus, it is 0.55, and then 0.36, 0.39, so highest again is P3. So of course these 3 values, the higher they are, the better it is for our packaging materials. But of course you cannot compare these materials with synthetic materials. Synthetic materials will be much higher. Maybe Professor Kanishka was showing the last year 80, 90 megapascal. Okay, so but in the biopolymer also 26 megapascal is pretty good actually. Then we wanted to characterize this stress relaxation properties by calculating this value. So percent stress relaxation, which will give you some idea of the viscoelastic nature of the films. Okay, so it is 67% in case of XG, but it reduced to 55.8% for xyloglucan. And because these films, they will have zinc oxide, so of course they will show antimicrobial activity, and that's what we are doing it. So we wanted to test it against 1 gram positive Staph aureus and 1 gram negative E. coli. Of course, these only polymers, they will not show any zone of inhibition. We did the zone of inhibition assay over here. So it was Staph aureus 11.12 millimeters a zone, or the diameter of the zone, then 12, and 12 is 9, 11, almost 12. Okay. So not much of a difference between the zone of inhibition compared to gram positive versus gram negative. So almost, because sometimes you will see gram negative is more resistant to antimicrobials because they have an extra outer membrane lipopolysaccharides, right? But in this case, we didn't see much of a difference. Okay, so that was in the film characterization, and now we wanted to really apply that in vivo. In food science, we call in vivo is to the food, not to the body. In vivo. So in vivo, we wanted to apply it to the real food. So we took tomato as a case study over here. So we took 3 samples. So first one was a control, which is uncoated. There is no coating at all on this. Then we took the JSS XG composite, the film 3, actually the 3rd combination, and the 5th one, that is ZLP3, because it was showing the best barrier property and the best mechanical properties. Okay? So we selected those 2 properties, and we could see that this one, of course, it was, I don't know if you can see, but this one was degrading. this one, this composite was also degraded in day. So you can see the day 12 compared, you can compare the day 12. Day 12 over here, which is zinc oxide nanoparticle 3, was at par with the control on day 3 or day 6, right? Day 0. So therefore, we concluded that ZP3 till day 12, day 15 it was showing some degradation, of course. Okay, but at least till day 12, there was good this in terms of the pictogram, the quality of the image was much better. So that is a visual representation. And then we wanted to quantify some basic physicochemical properties like weight loss percentage, hardness, okay, and the optical properties and color properties. So you can see that this is day 0, weight loss, there was no weight loss. But if you see that day 15, for ZP3, it was around 8 to 10%, okay, weight loss, okay. But in the control, the weight loss was much higher at 13.65 to 18%, much higher weight loss. But we could reduce that to 8.6 and 10% in terms of weight loss. Firmness also, if you see control 6.65, it reduced to 1.94 because the flute is, because over the storage period, you know, the tomato, it has a lot of pectin, right? The pectin will change from pectin to pectinic acid, and because there will be degradation of pectin. Because of that, the firmness decreases, right? But we could reduce that in the firmness also from 6.38 control firmness to around 3.94, this is 1.94. And the color values, if you see the L star will give you the whiteness index, okay? Not really whiteness, but will give you the idea of how much light and dark it is, okay? So therefore, control was 39. Here also day 0 it was 34, almost similar, but here it is 28 and 30. Okay, so we can say briefly it improved the lightness index. Same for Easter. So with that, we concluded that ZP3 was the 3% nanoparticle formulation was one of the best formulations. Okay. Now the second example that we will talk about is okay. So previous one we extracted the starch and cytoglucans, but before that in 2020 we were working on a similar project where we took tamarind, the whole powder. Okay, at that time we didn't have the plant to extract powder or kernel powder, and we wanted to prepare antimicrobial packaging materials using geraniol. So this is not a nanocomposite, this is a normal composite film using geraniol. Geraniol is another very important bioactive compound obtained from a lot of plants like your cumin and rose, lemongrass or this type of things. And geraniol is also it's a very powerful antimicrobial compound, which is it's also US FDA approved. So whatever we are using, it has to be US FDA approved. US FDA approved, okay? Otherwise there will be trouble. So we wanted to prepare again dispersion. So we have film forming solution. Then we have this 5 film forming solutions or emulsions, basically emulsions. We have 0.5% geraniol, 1% geraniol, 2% geraniol, and 3% geraniol. So the pH ranges from 5.68 to 5.94. And initially we didn't have the rheometer, so we just use a texture analyzer to calculate the viscosity. So it's around 0.191. It increased to 0.255 with the addition of the oil. We convert weight. And then we wanted to characterize and wanted to see how these geraniol oil droplets were distributed within the emulsion. So how the emulsion was formed. So we did the confocal laser scanning microscopy of this of the film forming emulsions. This is film forming emulsions. So this is your control. Control does not have any geraniol, so it is totally black. So we used a dye which is called fluorol yellow dye, which is a lipophilic dye, to observe these droplets. Okay, so droplet is a big droplet over here. This 0.5%, then 1%, 2%, 3%. Lot of droplets because the concentration is more. Then you have these are the pictographs of the films. This control, and we add the geraniol, it becomes more yellowish. Okay, this is 3% film. Then we have again the characteristics for thickness, moisture content. So of course, this because geraniol is highly hydrophobic or lipophilic, the moisture content reduces 30 to 21 and water solubility 35 to 18%. Then we have the optical and the surface properties. We characterize these mostly the optical properties, and then the contact angle. So contact angle increased from 41.6 in the control TKP film to 76 degrees, 76, okay, almost 77 in the case of 3% geraniol. Then we also studied water vapor transmission rate. Okay, so barrier property, water vapor barrier property control was 84.7. It reduces to 48. There is a significant reduction because of addition of geraniol. Okay, tensile strength. Okay, so another thing is when you add this oil, there's a compromise that has to be made because the oil behaves as a plasticizer. Once the oil behaves as a plasticizer, the mechanical property there is some compromise with that. Okay, so you have to. So that's why people want to combine both nanoparticles and oils at the same time. Okay, so when you add both the thing, you can have a more better formulation. Okay, in terms of mechanical properties. So 19.61 to 7.52 there was a reduction. Okay, Young's modulus also there was reduction 579 to 180.6. Puncture strength 5595 to 3852. Okay, stress relaxation was 67.4, but it increased quickly to 72.9. This was the environmental scanning electron microscopy of the films. Okay, control film, and then this is a 3% film. Then you have CLSM of the films also. This is that previously was for the emulsion. This is for the film. Again, there is no oil over here, and you can see the high oil density at the 3%. So this image also shows that your oil was retained after the film preparation process, and so it will show good antimicrobial activity because the yellow droplets are still present, right? This was FTI characterization. Again, this is for first one is for the oil, the geraniol alone. This is for the control film, and then 0.5%, 1%, 2%, 3%. Okay. So pretty similar type of profiles. XRD profiles again very similar. This is film the control film, and then the geraniol loaded films. Here the peaks are more amorphous because of course this TKP alone is very amorphous material, and geraniol will be larger. So if you had a nanoparticle, you will have sharp peaks, but that is not the case here. So you will have very amorphous and plain type of peaks. Okay, no sharp peaks. And then finally, we wanted to do the antimicrobial assay against Bacillus. The first one was Bacillus cereus, and the second one was Escherichia coli. Okay, so you can see as you increase the concentration, at the time zero itself, you can see there is a more increase in the zone of inhibition of Bacillus versus E. coli. Okay. So with that, I want to conclude that edible films and coatings is a novel technique. That's a novel, not really a novel, but it's a good technique in food science. And nanotechnology inspired systems demonstrates improved performance. So preparation nanocomposites is coming up in a big way, and a lot of work needs to be done in that area. Research involves techniques from biophysics and material science. That is one of the most good part that what I love is application of these techniques to study food materials. And antimicrobial food coatings and nano coatings is one of our most powerful and versatile technology available currently, which can be used as an alternative to conventional food processing techniques. With that, thank you. If you have questions.
Thank you, sir. It was such a nice presentation for delivering information about the sustainable application of agricultural byproduct in the field of food packaging. If anyone having questions, you may ask to speaker by raising hand, or you may write the question on the chat box. Please.
Sir, we are designing antimicrobial packaging. So if we apply the product, immediately it will act as the antimicrobial, it will release the antimicrobial agent, or we can control the release of antimicrobial agent.
Okay, so it's a very good question. So what we are doing is we are trying to entrap those molecules within the polymer. Okay, so there are different ways. So if you want to really entrap it in a more better way, you have to go for creating more like cross-links. Okay, more creating bonds like ionic bond or covalent bond. Okay, so what we are doing is mostly hydrophobic interactions, or what we have. We are not studying that, but because these compounds are hydrophobic, so they will be mostly there because of hydrophobic interactions. They are held within the polymer matrix. But if you want to do a more controlled release, then you might have to go for a better entrapping of the molecule within the polymer matrix, and only you can see a good controlled release.
That's okay. So how can we design the packaging film based?
So you have to so you can use like cross-linking agents, for example. A lot of cross-linking agents can be used to entrap your molecules within the polymer matrix. Okay, there are at this point I don't remember exactly the name of cross-linking agents, but there are a lot of papers on that cross-linking agents. Okay, so that is one of the good areas. I mean, good way to enhance the concentration of the polymers within the polymer matrix. Okay. Yeah. Well,
Sir, because of starch-based films, how can you, like, how are you trying to increase the hydrophobicity? Are you making any surface?
no, we are not doing that. But of course, if you want to make the starch more hydrophobic, so there is one of the most common reaction, that is octenyl succinylation. Okay, octenyl succinylation. So you can buy a compound which is called starch octenyl succinate. Okay, from companies you can buy that. Or you can prepare that in a lab also. You can take octenyl succinic anhydride and you can modify starch. Okay, so there are a lot of other modifications also, like oxidized starch, a lot of things are there. But this modification is approved by US FDA to be used in food. That is called starch octenyl succinic anhydride, or starch OSA. It's very common, starch OSA. If you are drinking your beverages, any beverages, cold drinks or this type of things, because these are also emulsions. Cold drinks are emulsions. So those emulsions, the flavor compound in that emulsion is stabilized by starch OSA. So starch OSA is one of the most common hydrophobic emulsifier that we used, but starch OSA has also got good film forming properties. Okay, so OSA is one of the major compound that can be used, and that is only till 3%. You cannot go beyond 3%. Okay? US FDA states till 3% it is safe to be used in for food applications. Okay, you can just go to US FDA website. There is a list of ingredients for which can be used for food materials and which can be used for food packaging material. So if you go to the US FDA website, all the list is there. Okay.
Since you are using zinc nanoparticles, does it have
Zinc oxide.
Zinc oxide. Does it have any long-term effect while consuming in the
Okay.
country?
Zinc oxide also people say it is safe till this 3% or 5%. Till that people are, so mostly it's US FDA approved. Okay. So beyond that, maybe there is long-term toxicity, maybe there. So nowadays people don't like metallic oxide nanoparticles. That is also one big challenge. Okay. But zinc oxide, at least till 3 or 5%, it is US FDA approved.
So can you again explain the parameters that you need to be taken into account in the development of edible vitamins? What are the parameters?
Okay. So when you are preparing when you are first preparing, so what technique we use is the most common technique and simple technique, that is solution casting or solvent casting technique. Okay. Of course, there are other techniques like extrusion. People use extrusion to prepare biopolymeric films. We don't have that technique here. So when you are preparing that, you have to consider the type of biopolymer you want to use. Okay, so mostly again, as the previous person said, that most of the biopolymers in food, they are hydrophilic, right? Because they have a lot of hydroxyl groups, they will take part in hydrogen bonding. So therefore, you want to use polymers which, so as he said, we want to make it more hydrophobic. Okay, hydrophilic polymers, there is a problem. So one way to reduce the hydrophilicity is you can combine different polymers. Okay, so you can combine like polymer A plus polymer B. You can do that as composite, or you can add the nanoparticles. Nanoparticle addition also reduces your hydrophilicity. Okay, or you have to go for modification of polymers. Okay, that is one. Second is when you are preparing the films or for the film, the two parameters that we said the most important will be the barrier property and the mechanical properties. Okay, those two must be checked first. Okay, so when you prepare the films, we first have to check the tensile, for example, tensile strength, then your Young's modulus. Okay, these two are most important: tensile strength, Young's modulus, and barrier property. What we use is the water vapor transmission rate. Okay, so there is a simple ASTM approved method which is possible to be done in the lab. Of course, if you have more better systems like water vapor transmission rate meter, okay, which is very expensive, more than 50 lakhs, then you can get more accurate data, but we don't have those capability here. But you have a more simpler technique called ASTM method. Okay, ASTM based WBTR testing method, cup method actually, which our students can also show you. We have our students here. So that type of technique can be used for calculation of WBTR. Another thing is called oxygen transmission rate. Professor Monia was showing that OTR, but we don't have capacity to measure OTR. But if we can measure the OTR also. Okay, so barrier mechanical in terms of the film properties, and then the application. How you want to apply that? Whether you want to apply that as a wrap, or you want to apply that as a coating, or you have to apply it as a dip, and that is based on the type of the food, right? So mostly what we are doing is for solid food, wrapping is a problem. You cannot prepare the film and wrap a tomato. That is not possible. It will just open up, right? So therefore, we have the challenge there, and we have to use the dipping method. We prepare the emulsion and we dip it. But if you want to preserve like paneer, like cheese, these type of things, then maybe wrap is also a good option. Okay, so based on the type of application, type of food, also you have to design your polymers with this packaging material. Okay, so this type of things you can. I mean, these are the basic things which you can consider by preparing biopolymer films.
So is glycerol the only plastic?
No, there are a lot of materials, glycerol, sorbitol, all these sugar alcohols. Okay, so they have good xylitol. Okay, so anything which is a sugar alcohol, they can monosaccharides alcohols, they can have. Also, our lab, they have, my student Rahul, he was working on called eutectic solutions, right? So eutectic solvents can also be have a lot of applications nowadays.
Thank you, sir.
So,
Applying anything as a edible plastic, you mentioned there are 4 properties: biodegradability, active and barrier. This active and barrier are going to be in the same place. The
yeah, active means it is having the active compound. So this polymeric material will be like your host, and you have the guest molecule inside. Okay, like your drug delivery system, right? And biodegradation, barrier is the water vapor barrier or the oxygen barrier. Okay, because these polymers, suppose if the polymer is more crystalline, then you will have a good, more WBTR and better OTR, oxygen barrier property. If the polymer is more amorphous, like starch, then you will not have that. But if you modify the starch, or you have the starch packing, like the amylopectin structure, amylopectin is highly packed. So if you take like waxy starch is the starch which has only 100% amylopectin, there is 0 aminos. Then waxy starch kind of starches may have more barrier properties compared to normal starch, because you need the more packing packed structure or more crystalline structure. But those are 2 different things: barrier properties versus active properties. 2 different things. Okay. From which one? For this one. Migration of polymeric compounds. Okay. So migration study is a very difficult study. I mean, it has to be done in a long term, 2 to 3 month study. Whenever we submit papers, sometimes they say do migration study. We are unable to do that all the time. Okay, so if you want to study like zinc oxide, if you want to study zinc oxide, we do the coating, the food, then you need instruments like ICP or this type of thing, because you want to study how the zinc oxide is migrating over from the package to the food. Okay, so instead of that, for migration studies, I would say it's kind of difficult, and long-term study needs to be done, and you need high-end instruments like ICP, OES, or at least atomic absorption spectroscopy. Without that, you cannot quantify zinc oxide or any metals, right? So yeah, that's what it is. Commercial scalability of packaging materials. Yeah, so the food, so that is what we want to go ahead. That is the eventual ultimate goal, that if some company will be interested into taking up this technology or producing in a large scale. But at this point, we are more focusing on the lab scale academic exercise. But of course, food waste, as I have shown, that there are so many materials, so many options are there to explore, and a lot of materials can be extracted from the food waste, right? And because they have so many types of fruits, vegetables, so many things, right? And so commercial scalability is possible. Of course, it is possible, but we need to figure out that how it should be done. Okay, that is in the future, that is to be figured out. Could you please talk about the shelf life of edible packaging materials? So when you have coated the food with the edible package, of course, it must improve the shelf life as compared to the regular without coating, right? So as you said, the tomato regular one was degraded in 3 days or 4 to 6 days, but you can extend it to 12 days with the zinc oxide, at least from the scientific parameters that we studied. Okay, so of course it should have the good beneficial effects.
We are finishing our question answer session. Thank you, sir, for your informative presentation. Now I would like to request Professor Balasubramanian to present Dr. Sarkar with a memento as a symbol of gratitude. Thank you, sir. With this, we end our morning session of the workshop. I request all the participants to kindly join at 3:20 p.m. for the validated session. Our photo thanks and validated session will be started at 3:30 p.m. Thank you. Our launch has been arranged near the basement area. It will be started by 1 p.m. Good afternoon, sir.
Hi, good afternoon, madam.
Am I audible?
Yes.
Okay.
Madam, one request.
Okay, sir.
I've
Hello.
asked you to add my colleague for the screen sharing.
Okay. Sir, could you please share your slides for trial for starting?
Yeah, can you add my colleague, the other email address I posted here? So he will share the screen.
What is his name, sir?
Come again?
Could you please say his name?
I've posted here in the chat box.
Okay, sir. Please, please accept the invitation. Okay. Please share the screen. Yeah, it's perfect. Perfect. Can you stop sharing, sir? Fast. Good. Start. कोई नहीं Okay. A pleasant good afternoon to all present here. We are here for the valedictory session for the Karyasala 5 days high-end international workshop on integrating innovations with cost effectiveness for computing electromagnetic energy assisted food processing and packaging technologies. It gives me immense pleasure to thank you everyone directly or indirectly involved in this workshop. First of all, I would like to invite Mr. Ganesh Ahuja, the Managing Director at K. Ahuja Group. K. Ahuja Group. It is a group of passionate, innovative, committed young minds driven by an intuitive zeal with believer to transform, innovate, and optimize. It stands as a leading manufacturer and suppliers of a wide variety of industrial products and services, including food conveyance products, material handling equipments, mining products, and many more. It is the one of the India's leading providers of exotic spices and premium dry fruits in whole and processed form. Thank you, sir, for being here. I request Mr. Ganesh Ahuja to inspire us with his kind words. Over to you, sir.
Thank you very much for the kind introduction, madam. Good evening, everybody. Thank you for this opportunity. It's been great to be part of this program and get to learn so much from learned professionals from all over the world, from all different spheres of the industry. To give you a quick background about us, we are a fourth generation family-run corporation with expansive interests in spices, herbs, and value-added foods. We've been providing this since over 8 decades now. And we're headquartered in India. We've got some operations internationally in Indonesia, Sri Lanka, Madagascar, Dubai, and some other countries as well. Over the last few years, we've been striving to bring the farmer and consumer closer together and we've been developing new technologies, we've been developing new products to try and bridge this gap. What we are doing is we're doing some organic products, conventional products in whole as well as bulk and retail formats. We provide ingredient solutions, customized options, inventory management services, and a lot of co-packing services as well. Just to give you a brief background, India is one of the largest exporters of spices in the world. And currently we're doing about $4.2 billion worth of exports out of India. This includes value added and pure spices both. Pure spices in terms of numbers would be 1.76 million tons, which is by far one of the largest contributors in the world. The top 3 spices that are exported from India include chili, cumin, and turmeric. One of the biggest products for Indian exports is chili, and it is one of the most challenging and is absolutely apt for this kind of a forum. Apart from these products, India is also exporting a lot of cumin, spice oils, oleoresins, and together these constitute about 80% of the exports out of India. In the recent years, what we have seen is a lot of microbial detection and issues with Indian products that are going into the international markets, such as US, Europe, as well as Japan. And now recently joining that list is Australia. For example, Indian pepper has been flagged by most of these countries for a high microbial load and contamination issues. Salmonella is the most recent threat that has come up in the US, on the US side, which started from meats, prepackaged meats and fresh meats in the US. And now it has moved, now the FDA, which is the US authorities, has shifted their focus to spices. There have been at times wherein our consignments of all Indian exporters have landed on US ports, and only after reaching there, they've been rejected by the authorities. So it's a transit, what used to be a transit of 30-35 days from India to the US due to the pandemic and shipping related issues. That transit has now gone from anywhere from 60 to 90 days, which has compounded these issues. And it's not just the exporters from India that are being impacted, but even on the other side, the manufacturers and the retailers, even they are having to face a lot of problems. And very rare has there been an occurrence wherein products are being recalled by large brands, both Indian and international, which are retailing in the US. The challenges that we face are with the high costs of sterilization, lack of alternates, and ETO of late has become a huge no-no for these developed countries. So Europe has totally banned ETO use. America in some parts and parcels allows, depending on the product. Now, this also poses a challenge for us even more because certain products like chili have some sort of natural element of ETO, possibly because of them being fruit and ripening and being dried. So those detections come up even more and more. There are multiple layers of testing because of these kind of contaminations that have to be done both on the Indian side as well as the receiving country. One of the other challenges is that when we are doing non-ETO, which is the other two options that we have is the radiation and steam sterilization. Steam sterilization, of course, is the most widely accepted given its lack of traces, etc., that are left on the product. The product deteriorates. Given that these are low, the spices that we handle are in semi-dried form, having a moisture range of anywhere from 6 to 12%. These have a low moisture content. So when they're treated with steam and high temperatures, they tend to change the physical and aromatic characteristics. So if you see here, there is a picture of an unsterilized and a sterilized product of ginger. So it does change the color profile, which sometimes can be good, sometimes can be bad, but it's completely unpredictable. It depends on how it is handled, what is the exposure, etc. So there are wide factors even within the steam sterilization methods that are used or practices that are used. Likewise, in chili, chili is one product which actually becomes dark after the heat and humidity application, which comes from steam. So in some countries, it's acceptable, but it's closing the doors on most countries which are looks conscious. So if you have a, even at home, when we have a lighter or good looking product, it's more acceptable versus a dark or a discolored product. So that's a similar mindset most other across the world also have. Switch. So the industry really needs more and more of the kind of solutions that are being developed via this platform today, and everyone present in this on this forum is looking at developing or has developed. There is a huge potential on this. For example, ETO versus steam. ETO will cost 1/10 of what a steam sterilization or steam treatment would cost us. Likewise, the capex on steam is very high. So we need to move forward with solutions which do not alter the structure of the food product, because ultimately it's, the mindset is that it is going into the body and should not have any traces or do more harm than what is expected. So we need to develop some low capex solutions, lower than steam. I'm sure most of you know that steam sterilization equipment or capex would cost anywhere from $200,000 to $300,000 with a bare minimum capacity. There has to be ease of use because a lot of people in the industry are not too we are always handling multiple products and in multiple formats. So ease of use has to be there so that we can switch between products, handle multiple products, and get the desired result. And of course, needless to say, whatever we have learned in the past couple of years from our experience, trying different dehydration techniques, different drying techniques, and different sterilization techniques, we'd be very happy to share that today on this platform via Q&A, or please feel free to reach out to me also. And we're more than happy to promote whatever developments that there are. And once again, really thank you for this opportunity, and open to questions.
Thank you, sir, for your time and valuable input you have shared with us today. If anyone having questions, please ask, sir. नहीं क्वेश्चन यहाँ पे तो नहीं है ना क्वेश्चन.
Probably the benefits of not having questions in the last session of the entire program.
क्वेश्चन क्या है? क्वेश्चन क्या है? Sir, the question is typing by the chat box.
Sure. Typically, the cost of steam sterilization for 1 kilo of a product is ranging from 20 to 30 rupees, depending on the density. Multiply by that by 1,000, you're looking at, you know, couple of maybe 2 or 3 lakhs. Initial moisture content for the products that need to be sterilized is ranging from 6 to 12%. And any reduction in the steam sterilization of this moisture content is actually an added expense or a loss to us in terms of net kilos lost. So the real cost is actually much higher because we are unable to control the moisture loss in steam sterilization.
Sir, I have a doubt, sir. So, during the steam sterilization process, we have losses of color, especially for the chili. So, how we can prevent it?
Sir, I'm repeating my question. For steam sterilization of chilies, we have color losses. So how
That's
we
right.
can minimize that industrially and in a continuous process lines?
So chili will change color when too much heat is applied. So if there is lesser heat applied, it's ideal. What does escalate is in the case of steam sterilization, when you're applying moisture plus heat. So if there is, minimum moisture applied with, that would help.
So just a follow-up question from that. Sir, the many industries which produces chili powder, they are facing the same problem. And right now, what solution they are using is they are not making chilies powder first. First, they're sterilizing the chilies, and then in the next step they are converting into the powder using different mills, hammer mills and other mills. So the question is like, when we comes to regulatory agencies like US FDA and EU, so they do not allow it actually. After the sterilization, they want they want the product to be packed immediately aseptically. So how does industrially you solve the problems like this?
So that's a good question. US FDA or likewise authorities don't really control whether you're sterilizing pre-packing or when. What they're more concerned with is the final amount of microbial load when the product reaches their doorstep. So typically there are some people who do try and do these practices of sterilizing before and then packing, then grinding and packing it, but it does not hold too much value because the microbial load is again built up in process. Any process that happens can typically last from a couple of hours to a couple of days, depending on what the end packaging or what the complete process is like. Because the batch also has to be sterilized. The batch has to be standardized, sorry. The biggest challenge with agri commodities is non-standard products. So like no two people are alike. No two pieces of chili or pepper will be alike. So standardizing that batch, so it has to be bulk or blended again after processing, and then it goes into packaging. Good manufacturer will get the entire in, blend it, rebulk it, and then go in for final packaging. Otherwise, you'll have a lot of bag to bag or packet to packet variation. One packet will be good color, good size. The other packet may be a complete opposite.
Sir, I have another question. So, sir,
Sure.
generally export, spices from India and, the tropic countries to this, the other like European countries. But in European countries, when we export the products in winters for them. So at that time, like in India, we have like normal temperatures, but when it goes to European countries, they have very low temperatures. So when the product reaches them, the clumping of all those spices powders, it happens. It formed the clumps inside the packaging material, though it was good in India, but when it reaches to the customer, the problem is there. So how we generally, solve these problems?
So sterilization is the best way to solve it because it does tend to reduce the moisture, like steam sterilization or any heat applied sterilization, even infrared for that fact. If a product is dried well, packed well in airtight bags and then shipped, there are usually very low chances of it forming clumps. Also, not too much heat can be applied because spices have a naturally occurring oils inside them, which is what gives them the flavor. In some cases, it's volatile oil and total oil. It's a combination of both. The real clumpiness happens when the moisture load is slightly higher and the transit times are very high. Like I was mentioning, anywhere from 30 to 90 days. And they're all packed up, locked up in a container, and the container in transit is going through high temperature variances from literally 10 degrees or zero temperature in the night to as high as 60 and 70 degrees in transit. Because mind you, these are iron containers, steel containers, which are being shipped and open to. Am I audible?
Yes, sir.
So in the containers, because these products don't have any breathing and there are high temperatures, huge fluctuations. It can be a fluctuation of 30 to 40 degrees just in transit between day and night and in closed environment. That also promotes the product to get heated, release moisture, but in the night, it promotes the product to again recapture that moisture, and then there's condensation even within the containers. So that tends to damage the product a lot more if there is inherent moisture in it.
The next question is from one of the online attendees. So the question is, when the salmonella is detected in the spices, when it is exported to other countries, so do we have any testing before exporting the products?
So because pepper, for example, has become a big problem, authorities from the other parts of the world, instead of banning the products, what they've done is they've made it mandatory for the Indian authorities to test specifically for microbial load or salmonella before the product is shipped out. So we are required for it to be tested by either the Spices Board or the IEC, just like in milk. And only after we get a clean product or it fits the receiving country's requirements, they give us a health certificate, which means that the goods are fit for exporting.
Another question from one of our online attendees. So how can we minimize the loss of essential oils of spices during pulverizing?
Typically, there are very high-end solutions like cryogenic grinding, etc., which may not fit the requirement. But then we do tend to blend it with other products, or we do tend to use a slower grinding speeds, or use bigger mesh sizes within the grinders so that there's lesser heat generation, or just introduce additional air so that the product gets cooled faster during the pulverizing process.
So the
To
next
answer the
question is,
question, yeah, please go ahead.
is there a requirement of rapid cooling after sterilization?
Yes, rapid cooling is required after steam sterilization for sure, because otherwise, if the product continues to remain hot, it will first lose some moisture and then very quickly absorb moisture from the ambient environment, especially in coastal cities like Mumbai and Kerala, sorry, Kochi. This is a huge problem.
One more question is there, sir. What about spice irradiation?
So spice irradiation is allowed in specific countries on specific products. It is not widely accepted across the board, and it does leave traces on the food product.
Thank you, sir. Thank you, sir. Now we are finishing our question answer session.
Sure. Thank you very much.
We are honored to have you in our validator session of the Karyashala 5 days high-end international workshop. Thank you once again, sir.
Thank you very much. It's been a pleasure.
Now we are start our validatory session. I request Workshop Coordinator Professor Parag Prasad Sutar, Associate Professor and Head of Food Process Engineering Department, and Professor V. Arun Prasad, Assistant Professor of Food Process Engineering Department at NIT Rourkela, to kindly occupy chairs on the dais. Thank you, sir. Now I would like to invite Professor Parag Prasad Sutar, Associate Professor and Head, Department of Food Process Engineering, NIT Rourkela, to present the closing remarks. Over to you, sir.
So very good afternoon to all of you, and I heartily welcome Mr. Ganesh for giving a lecture and very great information. Thank you, Ganesh, very much. This 5-day workshop is coming to the end today, and I am 100% sure that most of the people online as well as the offline are fully satisfied with the level of the lectures as well as the depth of the lectures. And I would like to share you the thing that at the start also I told you about Mr. Ganesh also I told that this workshop was not designed by me. It was designed by the industry. One of them person is Mr. Ganesh. We had a lot of discussion. He had called me to the Mumbai also. and we were working on this micro sterilized technology, and still that problem was not solved, and they are now using the steam sterilization, but still he is forcing a lot to, and he is saying that you have to develop alternative technology to the steam sterilization. So already there is a gamma radiation available, but it is having a lot of limitations and it is not easily available to all products. And processor like Mr. Ganesh Ahuja, they have very large amount of volume of the spices, and they buy most of the spices from the Sri Lanka, and they export to the USA, and they have offices in the Dubai, Sri Lanka, India. So looking into the India problems, and nowadays sterilization is a very, very important parameter. So food safety was one issue, and at the same time, so many quality characteristics during the processing of these spices and other products, that was equally important. So we cannot forget about the quality. So combination of both has to be completed, and that's why we were discussing a lot continuously, and then we decided to go with this one workshop, five days workshop, and we got a very good lecturers also. So out of them, we had very good lecture from Pennsylvania State University, then cold plasma expert from China Agriculture University, then ICT Mumbai. They are working on the cold plasma also. Lot of experience was shared by them, and they shared the really data. That was very important. And in our workshop, not from India, from South Africa also, there are some participants, and they are listening to this very seriously. And throughout the all lectures, you might have seen that there is always attendance high, online as well as here offline. So, Mr. Ganesh, I would like to add here that here we have got the fantastic combination. Yesterday also I told Masters Food Technology batch of ICT Bhubaneswar campus. Then here Masters Food Technology batch first year, second year PhD Food Technology and Food Engineering, as well as the IIT Kharagpur. All are together. That's why you will see that so many questions are coming. And in all sessions, almost half an hour, even 45 minutes, the question answer session from online as well as the offline was going on. And online also we saw that many, I know the industry people, they were there. So here there were a lot of good lectures from the on the micro processing, micro drying also, infrared peeling, infrared heating, infrared sterilization, then packaging technologies. One of faculty from the IIT Kharagpur who was very expert, as well as from our NIT, there were two packaging experts, Professor Pritam Sarkar and Professor Paul. They also delivered their research output in the packaging technologies, advanced packaging. Then Professor Ramaswamy, Professor Deshmukh, Professor Annapure, who is the director of ICT Mumbai, Professor Balasubramaniam, who also is in the NIT Rourkela. So there were so many high quality lectures, and not a single lecture was missed by our participants. And in this lecture, there were the participants who were from the big industries also, DS Foods, S4S Technologies, and many other professors were there. So with this, I thank you everyone who attended this workshop, online, offline. Now it's a time to tell everyone that success of this workshop was not due to just a simple arrangement. It needed a day and night extreme hard work by the research scholars of my lab. So out of this, first I will start with the Chinglin, Piyush, Durgavati, Adarsh, Padmesh, Abhipriya, Saurabh, Deepika, and many other PhD students, master's students all they work day and night, and they are here coordinating the online and offline both, which was the another challenge. So offline was okay, but same coordinating online, it was a very big challenge, and we found that. But anyway, our students, they have done it. I am very much thankful to Professor Arun Prasad, who is the co-coordinator of this workshop. Honestly, I would like to tell that when there was an application, I was not in that mood to apply and fill up all the forms and everything. Arun Prasad sir filled the all forms, everything. We got the lectures. She designed properly everything, and then we submitted. So I would like to tell you that I was little bit lazy, but Arun sir, he did everything. He said that you don't worry. So maximum credit goes to Arun sir. So with this, I would like to thank you all for great support, and most important thanks to Karyashala DST SARC sponsorship, because they had given the sponsorship with the condition that go offline and full funding has been given. So no Karyashala or no funding agency gives like this, and they gave the full funding after seeing the all lectures and our program. There was immediately money transfer. So extremely thankful to Sir and Karyashala for their support. Also, this FTBI building and our director, our deans, they gave us so many facilities, because this building is fully dedicated to programs like this. Here you can see that special boardrooms are available for the continuous working and the continuous handling of the programs, and with a very good arrangement that without that institutional support we cannot do it. So that credit also goes to the institute and FTBI building, and many other people who from the other department also supported continuously. Without that, it was not possible. I am thankful to Professor Pradhan, Professor Sabyasachi Mishra, Professor Poonam, Professor Sushil, Professor Gul, Professor Vinny, Professor Rachana. All of them, they supported continuously me in the arrangement of these workshops. Because there was a limited space in this room. This room is occupied, and many people from our institute also, they were forced to attend online, even if they were in another building. So for them also, I am very much thankful for helping me. And if anybody is remaining, for them also, I am very much thankful. And I hope with this, there is one small announcement also, that the same group of these experts, we are arranging this 11th Asia Pacific Drawing Conference in the Kolkata. So I would like to just give 2 minutes, because this announcement is necessary, because this workshop was one practice session of that international conference. Professor Muzumdar also instructed from. Okay, so I'm sharing the screen. Google. So you can see that it's the 11th Asia Pacific Drawing Conference 23, Innovations in Drawing Technologies for High Value Products and Sustainability. It will be held in Science City, Kolkata, West Bengal, February 18 to 19, 23. So this 10th Asia Pacific Drawing Conference was also organized by us in the Vadodara, and after that huge and great success, this conference international came again. Go back. Came again to us, and you can see. Go back. You can see that there are the topics. I would like to give the little bit information about the topics. Left hand, topics and speakers. So these are the topics: fundamentals, modeling, simulation, physical properties, product quality, process intensification, different drawings, everything. Special section will be also drawing industry work. And confirmed speakers are Professor Arun Majumdar, Professor B.N. Thora, Professor J.B. Naik, Director of ICT Jalna. It is Jalgaon. Professor Digvir S. Jayas, he has also confirmed. Xiao Dong Chen, he is a top professor in the China. Hong Wai Xiao, he is also confirmed. Professor H. Ramaswamy from McGill University. Ms. Vijal Matkar, Director of Solvay Research and Innovation, Vadodara. Professor T. Language, Dr. Kamlesh Patel from Melbourne. Professor Minjan, Professor Shyam Sablani, Mr. Nishan Garg, Professor Yoshi Dupami, Vesh Bhandari, Professor Vesh Bhandari, Queensland, Australia. From China, Professor Wu, Professor Vijaya Raghavan, Professor Patrick Pere. So these are already confirmed keynote speakers. They are trying to come to India. Maximum they are taking their reports to come to India, and there will be the big sessions. And under these different sessions, around 14 to 15 sessions will be there, and different papers will be presented and published. Some of the selected papers will be published in the drawing technology. Go to the first page. Bottom of the screen. These are the supporting industries. Out of this, Kia Ahuja group is also one of the supporter. So, and Drawing Technology Journal is already supporting us for a special issue. So selected papers will be published in the Drawing Technology, and that will be the panelist. So I request most of people, please try to submit. And this also event will be hybrid mode, because at that time we don't know people will be able to come, but everything will be fine at that time. Okay. So with this, I would like to end my talk, and thank you once again for all.
Thank you, sir, for your speech. Now I would like to request from our participant, Ms. Sangeeta from IIT Kharagpur, to deliver her thoughts regarding the workshop.
Very good afternoon to all the present here. First of all, I'd like to thank the entire coordinating team to give the opportunities to participate in this high-end workshop. And the coordinating committee, they have put all the effort in the busy schedule to bring all of us together in a single platform to further enhance our knowledge, both online as well as in the offline. Thank you, sir. And they have selected the speakers all over the world who's expert in the particular field, and the speakers were very interactive and engaging. They have we cleared all our doubts by the frequent interaction with the expert. So thank you all the expert, all the speakers who enlighten our knowledge further in the particular field. From the all over the workshop, I would like to highlight few topics which is similar to my research area. That is that infrared assisted peeling and microwave and radio frequency for insect infestation, and microwave for egg sterilization, and the applications of cold plasma for drug delivery systems and all the application point in the cold plasma system. So these are very interesting topic, and before coming here, I have a few general questions that I couldn't find anywhere for the answers. So after coming here, after interacting with the expert, I could able to clear those doubts. So thank you for all the entire teams who make this platform very useful and very effective in a valuable manner. So similarly, I'd like to expert few interesting emerging technologies in the upcoming workshop. So thank you all the coordinating committee and the student organizing committee as well. Thank you so much.
Thank you, Sangeeta. Next, I call upon Ms. Jakia from ICT Bhubaneswar to deliver her thoughts regarding the workshop. Good afternoon, respected organizers, staff members, and all the participants. I am Zakia Bagwan from Institute of Chemical Technology, Indian on Campus, Bhubaneswar. First of all, I would like to thank our respected organizer, Dr. Parag sir and Arun sir, for organizing this fantastic workshop. I'm very delighted to be a part of it. Memorizing from day 1 to day 5, we have learned very different emerging technologies, which will be useful for our research work and many more activities. We have gone through various electromagnetic energy, assisted processing and packaging technologies. And from that, my area of interest was IR drying and fermentation. So I would specially thank Dr. Shivanand Shirkole sir and P. Subramanian sir for guiding me so nicely. And I'm glad to get connected to the very great speakers. And I love to be in touch with them for further assistance. And also, I'm sure that everyone present in this room, they are having various research areas and they are working on various research fields. And I'm very sure that every doubt of each and everyone has been cleared very nicely. And the way the well-structured workshop was there, it was very nice. From day 1 to day 5, the structure was the way it was structured, like right from everything, the speakers and how interactive sessions they took. First of all, considering our doubts, like where we attend various seminars and webinars, but we getting clear our doubts is very rare. So here what we got was we were clear of all our doubts, and I would really thank this platform for providing the best of it, and thank you so much. Thank you. Next, I would like to request Mr. Tarak from Department of Food Process Engineering, NIT Rourkela, to deliver his thoughts regarding the workshop.
Good afternoon to our respected HOD sir and Professor Arun Prasad and faculty members of Department of Food Processing Engineering, Rourkela. First of all, I would like to thank all the student coordinators and the participants who make it a grand success due to their active participation in offline and online mode, and also the topics covered in this workshop, that is high-end technology on drying technology, mainly electromagnetic assisted processing and drying technology. And as I am a scientist in Krishna Kendra UAT, and also I am doing my PhD here. So after leaving this place, I will try my best to use these physical technologies, which will be used by the farmers, because they are mainly the end users, and also because there is entrepreneurs, those who are coming from the ground level and the village level. So I will also share these technologies with them. and all the topics and the questionnaire section and everything and all the arrangements, it was very good. And one thing also I will tell, in each lecture, if there would be some more videos with the theory, then it would be better, so that as it is told that seeing is believing, so it would be more understanding for us. But all other things it is good, and we hope also in the future same new technologies which is will be beneficial for the farmers, entrepreneurs, and industries, and it will be available to the participants in the form of this workshop. And I would also thank to all the people, those who are attached directly or indirectly, and for this 5 days workshop. Thank you.
Thank you, sir. Now we are opening our feedback section for online attending. Please raise your hands. One of our online attending, Mr. Sadiq Yusuf, wants to give feedback. Now it's time. Now it's time to acknowledge and encourage the talents of participants by presenting mementos and certificate to them. I request Prakash Sutra, Professor of NIT Rourkela, to honor the participants with certificates and mementos. Okay. Please, sir. Bhavna. The participants I am now calling in their names. Bhavna. No. Kazal. Jakia. Sambhaji. Namrata, Nikita, okay. Now I request Professor V. Arun Prasad, Assistant Professor of Department of Food Process Engineering, NIT Rourkela, to honor the participants with certificates and mementos. Vimal, Kesaram, Srijita, Harsha, Venkatesh, Sheikh Mohammed Faisal, now I request Professor Poonam Singha, Assistant Professor of Department of Food Process Engineering, NIT Rourkela, to honor the participants with certificates and mementos. James Salim, Deepak, Aditya, Gyanamurthy, Sangeeta, Now I request Mr. Ganesh Ahuja, the Managing Director of K. Ahuja Group, to deliver the concluding remarks. Over to you, sir.
Thank you, madam. It's genuinely been a pleasure and honor to be a part of this workshop and got to learn so much more, and hoping that we continue to learn and people like us who are not technocrats get to know the latest technologies are being developed. Hopefully some of us can also take some inputs from us, and really looking forward to the new products and processes that will be developed by the future generation and through this platform. Thank you very much, Parag. Thank you very much for this opportunity.
Thank you, sir, for your valuable time. Now I would like to invite Professor V. Arun Prasad, Assistant Professor of Department of Food Process Engineering, NIT Rourkela, and also the coordinator of the workshop, to deliver the vote of thanks. Yes, sir.
Finally, we arrived to the validity session. There are a lot of people I have to thank in this particular moment. It gives me pleasure to thank all the good hearts who helped a lot in making this 5 days international workshop a grand success. And this 5 days international workshop integrating innovations with cost effectiveness and competing electromagnetic energy assisted food processing and packaging technology. The as per this name says, no, here at this last 5 days, we had industrialists or from various industry, and we had academicians from various institutions, and we had researchers from various institutions from India. So this platform, I'm sure this platform served as a bridge between the industrialists as well as the academicians to share their ideas, share their research thoughts. I have seen a lot of discussion on the lectures as well as off the lectures, during the lunch break, during the tea break. I have seen a lot of discussion between these industrialists as well as industrialists and academicians as well as students. So this thus solves the purpose of this seminar. So I thought for past 10-15 years, there are a lot of research going on in this particular field, electromagnetic energy and its assisted food processing technology. But a platform like this will provide an opportunity for the researchers to commercialize their idea or their innovation in industrial scale. And as well as industry is also in need of energy efficient processing technologies like microwave assisted drying or microwave assisted sterilization process or microwave disinfection process. So all these technologies are still in research papers. So to make it a commercial scale, a viable technology, this kind of platform and workshop will be helping. In that way, I think this particular workshop, 5 days workshop, is a grand success, and it was very nice to interact with industrialists from various industry and academicians from various institutions. And I can see a lot of active participants from the students. Usually in the webinar and workshop, we don't have much interaction. We don't see much interaction between the researchers or the speakers and the audience. But here, what I have witnessed is, I have seen a lot of interaction, especially each and every online participants or from the offline participants. Now I have seen a lot of interaction and even some argument going in between the researchers and students. So that is a good sign. We are sharing our idea. Probably that will take you or that will give you more clarity about the technology. So here at this point, I would like to thank all the research scholars from Food Processing Engineering Department in Rourkela who helped us in making this conference a great success, especially Piyush, Abhipriya, Durgavati, Deepika, Chinglin. So these students they worked a lot. So Paraksa was telling that I did a lot of work in this. In my place, these students made a lot of work in my place. I just guide them to do such small works. These people they dedicated themselves day and night. They arranged everything from the hall, dinner, lunch, the accommodation to the participants. So all these things, they made a lot of effort. So I just want to make a special thanks to all of them. And then our department faculty members. So they are another pillars behind this grand success, especially all the professors who helped us in arranging the lectures, those who delivered the lectures, as well as who motivated others to deliver the lectures, and some faculty members. Right from, I have to mention all their by names, but Professor Ramchandra Pradhan, Professor Mishra, and Professor Divyakant Setu, and Professor Poonam, Professor Sushil, Professor Madresh, who have helped us a lot in arranging the accommodation at the last minute. So I have to thank my colleagues, Dr. Rachna, Minnie Rathre ma'am, and Dr. Khalid Gul for their support. Without their support, this will not be possible. And then come to the sessions, the speakers of the sessions. In the first day, we had a very good session from SS Shrikole from ICT Bhubaneswar. He delivered a lecture on hybridization of microwave, infrared, and UV, and in sterilization technology. And then after that, we had a practical session as well, where he explained well about the working principle behind microwave sterilization technology. And then on the second day, we had a lecture from high power electromagnetic equipment development from Ramesh Shinde from Kiron Technology Mumbai. And then effective effluent free peeling method from Dr. Prakash Uttar. And then we had a fundamental and application of MIR, a lecture delivered from Mr. Vijay from Philips Global Business Services, Pune. And then third day, we had a first session with the application of infrared technology in drying technology from Nishant Garg from GEM Industries. And then we had another session with advanced infrared energy emitters and its application delivered from industries from Pune. And then we had a third session, nanoparticle and photocatalytic input processing application from Professor Paul from NIT Rourkela. And then another lecture is from packaging technology of microwave processing of food from Kanishka, professor from IIT Kharagpur. So all these lectures were very much useful for the students as well as the industrial participants. And then the fourth day, we had a complete dedicated day for cool plasma technology. First lecture is delivered from cool plasma as an energy on non-thermal technologies for food sterilization from a professor from Hongwei from China Agriculture University. The second lecture from Professor Ramaswamy Anandeshwar in advanced in microwave processing from Pennsylvania State University. And then the third lecture, we had a fundamental plasma technology and its uses in bacterial inactivation from a professor from physics department, Institute of Chemical Technology, Mumbai, R.R. Deshmukh. And then atmospheric cold plasma technology for food processing from Department of Food Process Engineering, ICT Mumbai. And then Professor U.S. Annapure from ICT Mumbai. And then we had a final day, we had two lectures from our Balasubramaniam from Biotechnology Department of Biotechnology from NIT Rourkela. And then Professor Preetham Sarkar, who delivered a wonderful lecture on biomaterials and its application in packaging technology. So we had a wonderful session. All the sessions are framed in such a way that it covers the nook and corner of electromagnetic energy and its application in food processing technology. I hope this you would have enjoyed this session and gained a lot of knowledge about these processing methods. And then finally, we have speakers who shared their feedbacks, the participants who have shared the feedbacks. From their feedback, I can see they have gained a lot of knowledge from the speakers, and thank you for them. I would like to thank Department of Food Process Engineering Department, NIT Rourkela, as well as the academic dean, as well as the director who permitted us to conduct this workshop, and then DST SERB, who sponsored this 5 days international workshop. So without their support, financial support, it would not be possible for us to make this possible. Thank you so much for everyone. And finally, I request all the participants, those who participated online as well as those who participated offline, to fill a feedback form which will be circulated to you shortly in online. And then if you have any idea, or if you have any thoughts in bringing up a conference like this, you can share your ideas, you can share your feedback in that form. And if you have any upcoming topics or upcoming areas to be covered in a workshop like this, you can also suggest it there. Thank you so much. I think it's a time to close the session officially. On behalf of the organizing committee, I would like to close this 5 days international workshop officially here. Thank you so much.
Thank you, sir. With this, we came to closer the Karyagala 5 days high-end international workshop on integrating innovations with cost effectiveness for computing electromagnetic energy assisted food processing and packaging technology. On behalf of the organizing committee of Department of Food Process Engineering, I once again thank you all the speakers, professors, participants, research scholars, and students for attending the workshop. Thank you all. Hello. Thank you, Mr. Ganesh Ahuja, for your valuable time and inputs. Thank you, sir.